In the closing decades of the 19th century, physics was considered a nearly complete discipline. The laws of Newton, Maxwell, and thermodynamics had provided a seemingly comprehensive framework to explain the workings of the natural world. Gravity dictated the motions of planets, electromagnetism explained light and electricity, and thermodynamics laid out the principles governing heat, energy, and the inexorable flow of entropy. Yet, beneath this polished surface, subtle anomalies lurked, signals of an impending upheaval in the foundations of physics. One such anomaly was found in the study of blackbody radiation, a phenomenon that would lead Max Planck, a relatively obscure German physicist, to conceive of a constant that would forever change our understanding of the universe. A blackbody is an idealized physical object that absorbs all incoming radiation and re-emits energy in a characteristic spectrum determined solely by its temperature. By the late 1800s, experimentalists had measured the radiation emitted by heated objects with remarkable precision. They noticed that classical physics, specifically the laws derived from electromagnetism and thermodynamics, could predict the radiation spectrum only at lower frequencies. At higher frequencies, the theoretical predictions diverged catastrophically from the experimental observations. This glaring discrepancy became known as the ultraviolet catastrophe, a problem that haunted physicists and exposed the limitations of classical theory. Max Planck, born in 1858 in Kiel, Germany, was a man of meticulous intellect and quiet determination. He had been trained in the classical tradition, steeped in the successes of Newtonian mechanics and the emerging field of thermodynamics. Planck was not initially a revolutionary. He did not set out to overthrow classical physics or to challenge the centuries of accumulated knowledge. He was, above all, a problem solver, drawn to the rigorous mathematics that underpinned the physical world. His focus on blackbody radiation was driven not by a desire for fame or controversy, but by the intellectual challenge posed by the inability of existing theories to account for observed phenomena. Planck approached the problem with a combination of physical intuition and mathematical precision. He was particularly influenced by the work of Ludwig Boltzmann, whose statistical interpretation of thermodynamics had introduced the notion that energy could be understood in terms of probabilities and the behavior of large numbers of microscopic particles. Boltzmann's ideas were revolutionary in their own right, but Planck would take them further, extending the statistical approach to the emission of electromagnetic radiation. This conceptual leap required him to imagine energy not as a continuous flow, but as quantized, emitted in discrete amounts that could be mathematically modeled. The critical moment came in 1900 when Planck made a daring assumption. To resolve the blackbody radiation problem, he proposed that the energy of oscillators atomics, scale entities within the walls of a blackbody, could only take on discrete values proportional to the frequency of their vibration. The proportionality factor, an unknown constant, became the centerpiece of his groundbreaking work. He expressed this relationship through the now famous equation E equals h nu, where E represents energy, nu the frequency of the oscillator, and h the constant that would bear his name. This simple-looking equation encapsulated a radical idea. Energy, at the most fundamental level, was not infinitely divisible, but came in indivisible packets, which Planck called quanta. At first, Planck himself did not fully grasp the revolutionary nature of what he had done. He viewed his introduction of energy quanta as a mathematical trick, a convenient way to reproduce the experimental blackbody spectrum without abandoning the well-established framework of classical physics. He remained, for several years, a cautious figure, hesitant to claim that the universe itself adhered to this new quantized reality. But the empirical success of his formulation could not be denied. Planck's radiation law, incorporating his constant, precisely matched experimental data across all frequencies, resolving the ultraviolet catastrophe and establishing a new benchmark in theoretical physics. Planck's constant h was tiny 626 x 1034 joule seconds, but its implications were enormous. It represented a fundamental scale at which the classical notions of continuous energy ceased to apply. While the everyday world, governed by energies vastly larger than this scale, appeared smooth and continuous at the atomic and subatomic level, energy was inherently granular. The universe, in its deepest structure, was no longer a seamless continuum, but a lattice of discrete quanta, and Planck's constant was the key that unlocked this hidden architecture. The story of Planck's constant cannot be separated from the broader scientific milieu of the time. The late 19th and early 20th centuries were a period of profound questioning and experimentation. Physicists were grappling with the dual nature of light, the mysteries of cathode rays, and the peculiar behavior of electrons in atoms. Planck's work intersected with these investigations, providing a theoretical foundation upon which future discoveries would build. Albert Einstein, for instance, would extend the concept of energy quanta to light itself, proposing that photons, light particles, also obeyed the quantization principle, thereby explaining the photoelectric effect and cementing the concept of quantum theory. Planck's personal and professional life also offers insight into the context in which his constant emerged. He was a deeply disciplined scholar, dedicated to both teaching and research, who valued precision and rigor over flamboyant speculation. His work on Blackbody radiation was part of a broader engagement with thermodynamics, electromagnetic theory, and the philosophy of science. He understood that a new constant, no matter how small, could have profound theoretical consequences. Yet he proceeded with caution, aware of the potential controversy and the inertia of established scientific thought. The introduction of Planck's constant marked a pivotal turning point in physics. It was more than just a number. It was a symbol of the transition from classical to quantum thinking. Classical physics had assumed that energy could vary continuously, and for centuries, this assumption had sufficed to explain the natural world. Planck's insight shattered this assumption, revealing a hidden granularity in the very fabric of reality. The constant itself became a bridge between theory and experiment, providing a precise mathematical tool to describe phenomena that had previously eluded understanding. Understanding the origin of Planck's constant also requires appreciating the philosophical implications of the quantization of energy. For centuries, science had operated under the assumption that the universe was deterministic, predictable, and continuous. The introduction of quanta suggested a universe governed by discrete, probabilistic events at the smallest scales. This shift challenged not only the mathematics of physics, but also the philosophical conception of reality itself. Planck's constant thus represents a profound intellectual turning point, a moment when the universe revealed itself to be stranger, more intricate, and more astonishing than previously imagined. Moreover, Planck's constant was not merely a theoretical curiosity. It provided a new lens through which to interpret experimental data. Spectroscopy, thermodynamics, and later, quantum mechanics all relied on the constant as a fundamental parameter. It enabled scientists to calculate the energy levels of atoms, the emission spectra of materials, and the probabilities of quantum transitions. Without Planck's constant, the detailed, predictive framework of modern physics would be inconceivable. In the years following its introduction, Planck's constant gained recognition not only for its explanatory power, but also for its unifying role in physics. It appeared in the Heisenberg uncertainty principle, which quantified the fundamental limits of measurement at the quantum scale. It underpinned the Schrödinger equation, governing the evolution of quantum systems over time. It became a cornerstone of quantum electrodynamics, quantum field theory, and modern cosmology. Its reach extended far beyond the original problem of Blackbody radiation, touching every domain where the quantum world governs behavior. Planck's own reflection on his discovery is telling. He remained humble about the magnitude of his contribution, insisting that he had stumbled upon the idea almost reluctantly. He referred to the quantization of energy as a desperate act of mathematical necessity, rather than a deliberate challenge to classical physics. Yet history would judge differently. The constant that bore his name became one of the most profound symbols in science, representing the discrete, quantized nature of energy and signaling the dawn of a new era in our understanding of the universe. To fully appreciate the origin of Planck's constant, one must recognize the convergence of historical, experimental, and theoretical factors. It emerged at a moment when classical physics reached its limits, when careful measurement exposed inconsistencies, and when a mind capable of blending mathematical rigor with imaginative insight confronted an insoluble problem. It was the product of intellectual patience, meticulous experimentation, and a willingness to entertain radical possibilities. In doing so, Planck not only solved the problem of Blackbody radiation, but also opened the door to a new universe, one governed by quantized energy, probabilistic laws, and profound complexity. As the first keynote of our exploration into Planck's constant, understanding its origin sets the stage for the subsequent journey. It reveals the human story behind the numbers, the scientific detective work that uncovered a hidden structure in reality, and the philosophical upheaval that accompanied the realization that energy is not infinitely divisible. Planck's constant, born out of necessity, curiosity, and insight, became the spark that ignited the quantum revolution, a revolution that continues to shape science, technology, and our understanding of the cosmos. The initial reception of Planck's idea was one of cautious curiosity mixed with skepticism. At the turn of the century, the scientific establishment was deeply invested in classical physics. The laws that had governed centuries of experimentation were precise, reliable, and elegant. They had successfully explained planetary motion, the behavior of gases, and the principles of thermodynamics. To suggest that energy was quantized seemed almost heretical, a notion that challenged the intuitive understanding of continuity that scientists had taken for granted. Many peers regarded Planck's constant as a convenient mathematical construct rather than a fundamental feature of reality, a tool to fit data rather than a window into the true nature of universe. Despite this skepticism, Planck's work could not be ignored. The experimental data on Blackbody radiation were unambiguous, and the formula he derived using his constant fit the measurements perfectly. His equation accounted for the entire spectrum of emitted radiation, from low to high frequencies, resolving the ultraviolet catastrophe that had plagued classical physics. This success provided a compelling argument that there was something deeply correct about the underlying principle, even if its full significance was not yet appreciated. Slowly, the scientific community began to acknowledge that Planck's constant was more than a mathematical convenience. It was an empirical necessity, a constant of nature that demanded recognition. Planck himself remained cautious. He continued to present his ideas with the precision and humility characteristic of his work, emphasizing that his quantization was, at least initially, a theoretical device to reconcile theory with experiment. He did not immediately assert that energy itself was inherently discrete, aware that such a claim would provoke resistance and perhaps incredulity. Nevertheless, he laid the groundwork for a profound shift in thinking. By formalizing the constant mathematically and demonstrating its explanatory power, he created a foundation upon which others could build. The concept of discrete energy levels, which would seem extraordinary in 1900, became the cornerstone for a transformation in physics that would unfold over the next decades. The philosophical implications of Planck's discovery were profound. For centuries, physics had been governed by a deterministic world view, a universe in which causes produced effects with predictable precision and continuity. Newton's laws had epitomized this vision, portraying a cosmos where every motion, from falling apples to orbiting planets, followed exact mathematical rules. By introducing quantized energy, Planck challenged this continuity at the microscopic level. Although the macroscopic world still appeared continuous, the atomic and subatomic realms revealed a granularity that could not be ignored. Energy was no longer a smooth spectrum, but a series of discrete packets, each bound by the value of Planck's constant. The universe, Planck suggested indirectly, was far stranger and more structured than classical physics had imagined. As the implications of this constant became more widely understood, other physicists began to explore its consequences. Albert Einstein, in 1905, extended the idea of quantization to light itself. He proposed that light, long understood as a continuous electromagnetic wave, could also behave as discrete particles, or photons, each carrying energy proportional to its frequency, again involving Planck's constant. This insight explained the perplexing phenomenon of the photoelectric effect, where light striking a metal surface ejects electrons. Classical theory could not account for the observed behavior, but with the concept of quanta and the inclusion of Planck's constant, the mechanism became clear. Einstein's work confirmed that Planck's constant was not merely an abstract number, but a reflection of reality at the most fundamental level, bridging the gap between theory and experiment and extending the quantum concept to the behavior of light. The introduction of Planck's constant also marked a turning point in the relationship between mathematics and physical reality. Before this, constants in physics often described macroscopic properties, such as the acceleration due to gravity or the speed of light. But Planck's constant had a uniquely microscopic significance. It set the scale at which classical notions of energy, time, and space began to break down, indicating that the laws of physics required a new framework when dealing with the atomic and subatomic domains. This realization opened the door to the development of quantum mechanics, a theory that would revolutionize our understanding of matter, energy, and the fundamental forces of nature. Planck's constant also introduced a new universality to physics. Unlike material properties such as density or conductivity, which vary from substance to substance, Planck's constant is the same throughout the universe. Its universality implied that the quantization of energy is a fundamental property of nature itself, independent of local conditions. This idea reinforced the notion that the physical laws governing atoms and photons are consistent across space and time, a principle that underpins modern physics and cosmology. The constant became a reference point, a bridge connecting the observable macroscopic world to the hidden microscopic realm, and a crucial parameter for experiments and theoretical models alike. The constant's impact extended beyond pure theory into the realm of technology. Understanding that energy exists in discrete units led to practical insights into the behavior of electrons and photons, influencing the development of semiconductors, lasers, and a wide array of modern devices. The ability to control energy at the quantum level has enabled innovations unimaginable to Planck's contemporaries, transforming communication, computing, medicine, and industry. What began as a solution to a theoretical problem became a foundation for the technological revolution of the 20th and 21st centuries. Planck's own life continued to reflect the thoughtful, disciplined approach that had characterized his work. He remained in academia, dedicated to teaching and research, and witnessed firsthand the gradual acceptance of his ideas. Over time, the broader physics community recognized the profound significance of his constant. Figures such as Niels Bohr, Werner Heisenberg, and Erwin Schrödinger would build upon his work, each developing key components of quantum mechanics that relied on the quantization principle he had introduced. Planck's constant became central to the Schrödinger equation, which governs the behavior of quantum systems, and to the Heisenberg uncertainty principle, which defines the limits of measurement and knowledge at the quantum scale. The simple, elegant constant that had originated in a study of Blackbody radiation became the bedrock of a scientific revolution. The conceptual leap that Planck made was remarkable not only for its immediate explanatory power, but also for the intellectual courage it implied. He confronted an experimental problem that defied classical theory and proposed a solution that, at the time, seemed almost counterintuitive. In doing so, he demonstrated the power of mathematics and theory to reveal truths about the natural world that were not apparent from direct observation. His approach illustrated a fundamental principle of scientific inquiry, that observation, experimentation, and theoretical insight must work together to uncover the underlying order of nature. In retrospect, Planck's constant represents both a specific scientific discovery and a symbol of a broader transformation in human understanding. It embodies the shift from a deterministic, continuous view of the universe to a probabilistic, quantized framework. It highlights the importance of careful observation, meticulous calculation, and the willingness to challenge established assumptions. It also underscores the interconnectedness of scientific progress. A single constant, discovered in the context of Blackbody radiation, would resonate throughout physics, shaping everything from atomic theory to cosmology, from quantum computing to our understanding of the origin and evolution of the universe. The journey from problem to solution, from the ultraviolet catastrophe to the recognition of quantized energy, demonstrates the power of intellectual perseverance and the interplay between theory and experiment. Planck's careful work, grounded in rigorous mathematics yet guided by physical intuition, transformed an abstract, puzzling anomaly into a principle that would illuminate the fundamental workings of reality. His constant, initially conceived as a means to fit data, became a lens through which the universe could be understood at its most elemental level. Even today, the discovery of Planck's constant continues to inspire and challenge physicists. It serves as a reminder that nature often defies intuitive expectations, and that careful, persistent inquiry can uncover truths far deeper than initially imagined. It is both a tool for measurement and a symbol of the profound complexity and elegance of the quantum world. Every modern calculation in quantum physics, every technological advancement rooted in atomic behavior, owes its existence to the insight encapsulated in this tiny, yet infinitely significant number. Planck's legacy is not only scientific, but also philosophical. His work invites reflection on the nature of reality itself, the realization that energy is quantized challenges assumptions about continuity, determinism, and the limits of human understanding. It opens the door to a universe that is at once orderly and surprising, predictable in some ways yet fundamentally discrete at its core. In recognizing the significance of this discovery, one gains not only a deeper understanding of physics, but also a profound appreciation for the subtle, intricate structure of the cosmos and the extraordinary human ingenuity that revealed it. At the dawn of the 20th century, physics stood on the brink of a transformation. Classical mechanics, electromagnetism, and thermodynamics had created a universe governed by predictability, continuity, and determinism. Newton's laws described motion with unerring precision. Maxwell's equations explained the propagation of light and electromagnetic waves, and thermodynamic principles outlined the flow of heat and energy. Yet, beneath this surface of elegant certainty, the universe whispered of deeper, stranger truths. It was a time when careful experimentation began to reveal phenomena that could not be reconciled with existing theory, signaling the emergence of a new framework for understanding reality: quantum theory. The journey toward this new physics was not sudden. It was the culmination of incremental observations, anomalies, and daring theoretical leaps. One of the most glaring puzzles of the late 19th century was the behavior of blackbody radiation. Classical physics, relying on the assumption that energy could vary continuously, predicted that the energy radiated at high frequencies would increase without limit. This catastrophic divergence, known as the ultraviolet catastrophe, indicated that something fundamental about energy and radiation had been misunderstood. Experimentalists, meticulously measuring the emission spectra of heated objects, found a pattern that defied classical explanation. The energy did not diverge. Instead, it peaked at certain frequencies and then diminished, a pattern that suggested hidden rules governing the microscopic world. Into this intellectual tension stepped Max Planck. Initially a conservative physicist, he sought a solution not by discarding classical principles, but by finding a mathematical framework that matched experimental data. His revolutionary idea was deceptively simple in its expression. Energy is not continuous, but comes in discrete units, proportional to the frequency of radiation. The proportionality factor, Planck's constant, became the linchpin of this radical proposal. By introducing quantization, Planck resolved the blackbody radiation problem, aligning theoretical predictions with experimental observations. The simplicity of the equation E equals h nu belied the profound implications. Energy at the microscopic scale obeyed rules entirely different from the smooth continuum assumed by classical physics. At first, Planck's approach was viewed with cautious intrigue. Many of his contemporaries saw it as a clever mathematical device rather than a statement about the nature of reality. Planck himself was hesitant to claim that the universe truly adhered to discrete energy packets. For him, quantization was a tool to fit data, a desperate act of mathematical necessity. Yet the implications of this approach would soon ripple through physics, challenging deeply held assumptions about energy, matter, and the fundamental laws governing the universe. Albert Einstein extended Planck's idea in a groundbreaking leap. In 1905, he proposed that light itself could be quantized, behaving not just as a continuous electromagnetic wave, but as discrete particles, later called photons. Each photon carried energy proportional to its frequency, with Planck's constant serving as the proportionality factor. This radical reinterpretation of light explained the photoelectric effect, a phenomenon in which light striking a metal surface causes the emission of electrons. Classical wave theory could not account for the observed threshold frequencies or the relationship between light intensity and electron emission. Einstein's work demonstrated that Planck's constant was not a mere mathematical convenience. It reflected a fundamental property of nature, linking the behavior of light and matter in ways previously unimaginable. The concept of energy quanta extended beyond radiation. Atomic physics began to reveal that electrons within atoms occupy discrete energy levels rather than moving freely within continuous ranges. Niels Bohr, in 1913, incorporated Planck's constant into his model of the hydrogen atom, proposing that electrons could only occupy specific orbits with quantized energies. When an electron transitioned between these orbits, it emitted or absorbed a photon whose energy corresponded precisely to the difference between levels, governed by Planck's constant. This model explained the discrete spectral lines of hydrogen, providing a clear demonstration of quantization in the atomic realm and solidifying the principle introduced by Planck. The emergence of quantum theory represented a profound shift in scientific thinking. Classical mechanics had treated the universe as a deterministic machine, where causes produced predictable effects and measurements could, in principle, be made with arbitrary precision. Quantum theory introduced a fundamentally different framework. At the microscopic scale, outcomes are probabilistic, energy is quantized, and certain quantities, such as position and momentum, cannot be simultaneously measured with arbitrary precision. Planck's constant serves as the scale for these quantum effects, defining the boundary between the continuous macroscopic world and the discrete, probabilistic microscopic realm. It is both a numerical value and a conceptual gateway, guiding our understanding of the atomic and subatomic domains. The development of quantum theory was not an isolated intellectual achievement, but a collaborative, cumulative process. Planck's introduction of energy quantization inspired a generation of physicists to explore the microscopic world in new ways. Werner Heisenberg, Erwin Schrödinger, and Paul Dirac built upon the quantization principle, formalizing the mathematical framework of quantum mechanics and extending its predictive power to increasingly complex systems. The probabilistic interpretation of quantum mechanics, encapsulated in Heisenberg's uncertainty principle and Schrödinger's wave equation, relies fundamentally on Planck's constant, highlighting its central role in the architecture of modern physics. Quantum theory also had immediate practical consequences. Understanding energy quantization allowed scientists to manipulate atomic and molecular systems with unprecedented precision. Spectroscopy, semiconductor physics, and the development of lasers all depend on principles rooted in Planck's constant. Technological applications from computers to telecommunications, from medical imaging to quantum computing, are direct descendants of the insights made possible by the quantization of energy. In this sense, Planck's work is not merely a theoretical milestone, but a foundation for the technological transformations that define the modern world. The philosophical implications of quantum theory are equally profound. By introducing energy quanta, Planck and his successors challenged centuries of assumptions about continuity, determinism, and the nature of reality. The microscopic world is not a smooth, predictable machine, but a landscape of discrete probabilities, where measurement and observation play a crucial role in determining outcomes. Planck's constant represents the scale at which this new order emerges, a bridge between classical intuition and the underlying quantum reality. It forces us to confront the limits of human understanding, revealing a universe that is at once orderly and astonishingly complex. The historical context of Planck's discovery adds further depth to its significance. The late 19th and early 20th centuries were a time of scientific ferment, when experimental precision began to expose the cracks in classical theory. Physicists were probing phenomena that could not be explained by existing laws, from the behavior of electrons to the emission spectra of atoms. Planck's insight came at precisely the right moment, providing a theoretical framework to reconcile these anomalies and setting the stage for a broader revolution. It exemplifies the interplay between careful observation, mathematical reasoning, and conceptual imagination that drives scientific progress. Planck's constant also introduced a profound universality into physics. Unlike material properties, which vary from substance to substance, Planck's constant is the same throughout the universe. It governs the behavior of atoms in distant stars, photons traveling across the cosmos, and particles in laboratory experiments on Earth. This universality underscores the fundamental nature of energy quantization and highlights the unity of physical law across space and time. In this sense, Planck's constant is both a numerical value and a philosophical statement about the coherence and consistency of the natural world. The process by which quantum theory emerged illustrates the iterative, collaborative nature of scientific discovery. Planck's work provided the initial spark, a solution to a specific problem in blackbody radiation. Einstein extended the principle to light, Bohr applied it to atoms, and successive generations of physicists formalized the mathematics and explored the implications for increasingly complex systems. Each step relied on the previous insights, building a comprehensive framework that explains phenomena across scales, from the microscopic to the astronomical. Planck's constant remains the thread that weaves through this tapestry, connecting disparate discoveries into a unified understanding of nature. Understanding the birth of quantum theory also requires an appreciation of the human dimension. Planck was a careful, methodical thinker, cautious in his claims yet bold in his reasoning. Einstein was imaginative, willing to extend principles into uncharted domains. Bohr was pragmatic, building models that matched experimental observations. The emergence of quantum theory was not a solitary achievement, but a collective endeavor, a dialogue across generations, shaped by experimentation, theoretical insight, and philosophical reflection. Planck's constant is the linchpin of this dialogue, the fundamental measure around which the story of quantum mechanics revolves. As the implications of quantum theory unfolded, the world of physics was transformed. Classical assumptions of continuity and determinism were replaced by probabilistic laws and discrete energy levels. Experiments that once seemed puzzling, from spectral lines to the photoelectric effect, found clear explanation. Theoretical tools, from Schrödinger's wave function to Heisenberg's matrices, were developed to predict and describe quantum behavior. At the heart of these developments lies Planck's constant, the key that unlocks the mysteries of energy, matter, and radiation. The influence of quantum theory extended beyond the laboratory. It reshaped our understanding of chemistry, biology, and materials science, providing insight into chemical bonding, molecular behavior, and the interactions of light with matter. The technologies that emerged from this understanding, transistors, lasers, superconductors, have reshaped society, economy, and culture. All of these innovations trace their lineage back to the quantization of energy and the introduction of Planck's constant, demonstrating the profound impact of a single theoretical insight. Quantum theory also reshaped philosophical perspectives on the universe. By showing that energy is quantized and that microscopic events are governed by probability, it challenged deterministic, mechanistic views of nature. The universe was revealed as a layered reality, continuous at the macroscopic scale, yet discrete and probabilistic at the microscopic level. Planck's constant is the numerical and conceptual boundary between these layers, the measure that defines where classical intuition gives way to quantum reality. Its discovery marked the beginning of a new intellectual era, one in which observation, mathematics, and imagination converged to reveal the hidden structure of the cosmos. The emergence of quantum theory demonstrates the interplay between theory and experiment. Planck's introduction of energy quanta was motivated by empirical data, a problem in Blackbody radiation that classical theory could not solve. Einstein's photon hypothesis was similarly driven by experimental anomalies. Bohr's atomic model was constructed to match spectral observations. Each step in the development of quantum theory exemplifies the delicate balance between conceptual innovation and empirical validation, with Planck's constant serving as the guiding measure. Throughout, the recognition of energy quantization also had profound consequences for the understanding of fundamental physical limits. It led to the realization that certain quantities, such as action, energy, and angular momentum, are discrete rather than continuous at the quantum scale. This quantization imposes limits on measurement, prediction, and control, fundamentally altering our conception of determinism and causality. Planck's constant defines the scale of these effects, linking the abstract principles of quantum theory to measurable physical phenomena. Its discovery represents a bridge between the observable world and the hidden rules that govern it. As the 20th century progressed, the implications of quantization became increasingly apparent, reshaping the entire landscape of physics. The initial insight that energy was emitted in discrete packets led to a cascade of discoveries, each revealing layers of reality that had been hidden from classical intuition. Physicists began to understand that the rules governing the microscopic world were fundamentally different from those describing everyday experience. Planck's constant, though small in magnitude, defined the scale at which these new laws became significant, acting as a boundary between the familiar macroscopic world and the strange, probabilistic quantum realm. Werner Heisenberg, in the 1920s, extended the principles of quantization to a rigorous mathematical framework. He recognized that the behavior of electrons in atoms could not be fully captured by classical trajectories. Instead, physical quantities such as position and momentum could not be simultaneously determined with arbitrary precision. The product of the uncertainties in these measurements is constrained by Planck's constant, forming the core of what became known as the uncertainty principle. This realization challenged the deterministic world you inherited from Newtonian physics. It showed that at a fundamental level, nature is probabilistic, not predictable, and that Planck's constant sets the scale at which this indeterminacy emerges. The constant thus became a measure of the universe's intrinsic graininess, a fundamental limit that governs the precision of all measurements in the quantum domain. Erwin Schrödinger, almost contemporaneously, developed a complementary formulation, the wave equation that bears his name. Schrödinger's equation describes how quantum systems evolve over time and relies on Planck's constant to quantify the relationship between energy, frequency, and temporal evolution. Where Heisenberg emphasized discrete measurements and matrices, Schrödinger emphasized continuous wave functions and probability amplitudes. Both approaches are mathematically equivalent, yet they highlight different aspects of quantum reality. In both cases, Planck's constant is indispensable, providing the numerical bridge that connects energy levels, frequencies, and probabilities. Without it, the predictive power of quantum mechanics would collapse. It is the thread that binds theory to observation, mathematics to reality. The application of Planck's constant also revolutionized our understanding of atomic structure. Niels Bohr's model of the atom, initially applied to hydrogen, showed that electrons could occupy only certain allowed orbits. Transitions between these orbits corresponded to the absorption or emission of photons, with energies determined by the difference between the quantized levels, again proportional to Planck's constant. This explained the discrete spectral lines observed in atomic emission spectra, resolving long-standing puzzles in spectroscopy. Later refinements, including quantum electrodynamics and the inclusion of electron spin and relativistic effects, continued to rely on Planck's constant as a foundational parameter, underscoring its universality and centrality in atomic physics. Beyond atoms, Planck's constant governs the behavior of molecules and larger systems. In chemistry, the quantization of energy levels explains molecular vibrations, rotational states, and the structure of chemical bonds. It allows scientists to predict reaction rates, energy transfer processes, and the absorption and emission spectra of molecules. Infrared spectroscopy, Raman spectroscopy, and nuclear magnetic resonance, all indispensable tools in modern science, depend fundamentally on the precise quantization defined by Planck's constant. In this sense, the constant is not merely a physical abstraction, but a practical instrument, shaping the way scientists probe and manipulate matter at the microscopic level. The development of quantum mechanics also introduced profound conceptual shifts. Classical physics had assumed that the universe could be described entirely by continuous variables, but the discovery of discrete energy levels forced a rethinking of foundational assumptions. Probability replaced certainty, and the act of measurement was recognized as an active participant in defining the system. Planck's constant sets the scale for these effects, linking energy, time, and frequency in a way that governs the behavior of all quantum systems. It is the measure of nature's granularity, defining the smallest meaningful action in the universe and dictating the scale at which classical approximations break down. The technological ramifications of this shift were immense. Quantum theory, anchored by Planck's constant, enabled the invention of transistors, semiconductors, and lasers, which form the backbone of modern electronics and communications. Without the precise understanding of quantized energy levels, these technologies would be impossible. Planck's constant, though introduced in the context of a theoretical puzzle, became the key to controlling and harnessing the behavior of electrons and photons. It provided the foundation for the digital revolution, enabling the development of computers, smartphones, and the global information infrastructure. In this way, an abstract constant from a laboratory experiment in Berlin over a century ago continues to shape our daily lives. Quantum theory also transformed our understanding of light. Prior to Planck and Einstein, light was primarily understood as a wave, a continuous oscillation of electric and magnetic fields. The quantization of energy revealed its particle-like behavior, introducing the dual wave, particle nature that underpins modern physics. Experiments such as the photoelectric effect, Compton scattering, and double-slit interference confirmed that light exhibits both particle and wave characteristics, with Planck's constant governing the energy of photons. This duality, strange and counterintuitive, is now central to quantum optics, photonics, and the study of fundamental interactions between light and matter. At the same time, the universality of Planck's constant highlighted a profound symmetry in nature. The same constant governs atomic transitions in distant stars as it does in laboratory samples on Earth. It underlies the behavior of subatomic particles in accelerators, the vibrations of molecules in living cells, and the energy levels of photons in the cosmic microwave background. This universality reinforces the idea that the laws of physics are consistent across the cosmos, a principle that allows scientists to extend quantum theory from laboratory experiments to the largest scales of the universe. Planck's constant thus serves not only as a numerical parameter, but as a symbol of the coherence and unity of natural law. The philosophical implications of these developments are equally significant. The recognition that energy is quantized and that uncertainty is inherent at the quantum scale challenges classical notions of determinism. It compels a re-evaluation of what it means to know the universe, suggesting that the very act of observation plays a role in defining reality. Planck's constant is central to this philosophical shift, providing a scale at which classical intuition fails and quantum principles dominate. It transforms our conception of reality from a smooth, continuous fabric into a discrete, probabilistic structure, where energy, action, and measurement are intertwined in ways that defy everyday experience. The theoretical frameworks built on Planck's constant also provided the foundation for a deeper understanding of the fundamental forces of nature. Quantum electrodynamics, quantum chromodynamics, and the Standard Model of particle physics all incorporate the constant as a fundamental parameter. It governs the interactions of particles, the structure of atoms and molecules, and the behavior of light and matter at the most elementary level. The precision of Planck's constant allows scientists to make predictions with extraordinary accuracy, from the energy levels of hydrogen atoms to the scattering of subatomic particles in particle accelerators. Its discovery, initially motivated by a problem in Blackbody radiation, became the key to a unified understanding of the microscopic universe. Planck's constant also played a pivotal role in defining natural units of measurement. By combining Planck's constant with the speed of light and the gravitational constant, physicists can define Planck units, which establish scales for time, length, mass, and energy at the quantum level. These units provide insight into the extremes of nature, from the smallest distances and times to the earliest moments of the universe. In doing so, Planck's constant becomes not just a tool for calculation, but a window into the fundamental architecture of reality, connecting quantum mechanics, relativity, and cosmology in a coherent framework. The influence of Planck's constant extends beyond physics into chemistry, materials science, and emerging technologies. Understanding quantized energy levels allows chemists to predict molecular behavior, design new materials, and manipulate chemical reactions with precision. In materials science, it guides the development of semiconductors, superconductors, and nanoscale devices. In emerging fields such as quantum computing and quantum communication, Planck's constant remains central, defining the limits of control, measurement, and information processing at the quantum level. Its impact is both theoretical and practical, bridging the abstract principles of quantum mechanics with transformative applications in the modern world. The story of the birth of quantum theory illustrates the interplay between observation, theory, and innovation. Planck's insight, initially a solution to a specific experimental puzzle, became the foundation for an entirely new understanding of the universe. Einstein, Bohr, Heisenberg, Schrödinger, and countless others built upon this foundation, formalizing the mathematics of quantum mechanics and extending its reach across physics and chemistry. Through all these developments, Planck's constant serves as the central measure, the numerical thread that ties together phenomena from the emission of photons to the structure of atoms and molecules. It is the constant that gives shape and coherence to the quantum world. The emergence of quantum theory also exemplifies the iterative nature of scientific progress. Initial discoveries raise questions, which in turn drive further experimentation and theoretical development. Planck's quantization led to Einstein's photon hypothesis, Bohr's atomic model, Heisenberg's uncertainty principle, and Schrödinger's wave mechanics. Each advance clarified and extended the principles established by Planck, revealing deeper layers of reality. Planck's constant remains at the center of this unfolding narrative, providing a consistent measure of energy, frequency, and action across all quantum systems. It is both a practical tool for calculation and a conceptual guide to the underlying architecture of nature. As quantum theory matured, it transformed our understanding of matter, energy, and the fundamental laws governing the universe. Discrete energy levels, probabilistic outcomes, and the interplay between observation and reality became central features of the physical world. Planck's constant defines the scale at which these features emerge, marking the boundary between classical intuition and quantum reality. Its discovery was not just a technical achievement, but a conceptual revolution, reshaping the way humans understand the cosmos, the limits of knowledge, and the fundamental principles that govern existence. At the heart of quantum mechanics lies a single, deceptively simple number, Planck's constant. Small in magnitude, yet vast in conceptual significance, it defines the scale at which the quantum world diverges from the classical one. Understanding this constant requires a journey through both abstract thought and empirical observation, a journey that illuminates the hidden architecture of reality and reveals the precision, elegance, and subtlety of the universe. It is more than a parameter in an equation. It is the thread that binds energy, frequency, time, and the very structure of the microscopic world. Planck's constant, symbolized as h, first emerged in the context of Blackbody radiation, a problem that classical physics could not resolve. In simple terms, it is a proportionality constant that relates the energy of a quantum to the frequency of its associated electromagnetic wave. Expressed mathematically as E equals h nu, it links energy E with frequency nu through this tiny but universal constant. The elegance of the equation belies the profundity of its implications. Where classical physics treated energy as a continuous variable, capable of taking any value, Planck introduced the radical idea that energy is fundamentally quantized, arriving in discrete packets, or quanta, each defined by h. These quanta form the building blocks of atomic and subatomic processes, establishing a granularity in the fabric of reality. To grasp the meaning of Planck's constant, it is instructive to consider its numerical magnitude, approximately 626 times 1034 joule seconds. The value is astonishingly small, which explains why the quantum nature of energy is not directly perceptible in the macroscopic world. Everyday objects, governed by energies many orders of magnitude larger than a single quantum, behave as if energy were continuous. Yet, at the atomic scale, where energy transfers are comparable to the magnitude of h, the discrete nature of energy becomes unavoidable. This tiny number, seemingly insignificant in daily life, defines the boundary where classical intuition breaks down and quantum principles dominate. The concept of quantization, encapsulated by Planck's constant, fundamentally altered our understanding of energy transfer. In classical theory, energy could be absorbed or emitted in arbitrary amounts. An atom could, in principle, radiate a continuous spectrum of energies. But Planck showed that this assumption leads to contradictions, most famously the ultraviolet catastrophe. By assuming that energy could only be exchanged in multiples of h times the frequency, Planck created a model that exactly matched experimental measurements. Each quantum is indivisible, a fundamental unit of energy that constrains physical processes at the smallest scales. This principle underlies the emission and absorption spectra of atoms, the behavior of electrons in molecules, and the probabilistic rules of quantum mechanics. Understanding why H is universal requires a consideration of its role in the structure of matter and radiation. Unlike material constants, which vary with the properties of substances, Planck's constant is invariant. It appears in phenomena ranging from the vibrations of atoms in a crystal lattice to the energy carried by photons traveling across the cosmos. Its universality implies that the rules governing quantum interactions are the same everywhere in the universe, providing a consistent framework for atomic and molecular behavior. This constancy is crucial for both theory and experiment, allowing physicists to predict phenomena across a vast range of contexts, from laboratory samples to distant stars. The universality of Planck's constant also extends to its role in defining natural units. By combining h with other fundamental constants, such as the speed of light and the gravitational constant, physicists define Planck units, which establish scales for length, time, mass, and energy at the quantum level. These units provide insight into the structure of the universe at the smallest scales and the earliest moments of cosmic history. Planck's constant thus serves as a bridge between the observable world and the underlying quantum architecture, linking fundamental constants to create a coherent, self-consistent system of measurement that transcends everyday experience. At a conceptual level, Planck's constant represents the graininess of nature. It defines the minimum action, the smallest meaningful product of energy and time, below which classical notions of continuity cease to apply. In this sense, the universe is not a seamless continuum, but a mosaic of discrete interactions, each bounded by h. The implications of this insight are profound. It sets the scale for the uncertainty principle, determines the spacing of energy levels in atoms and molecules, and governs the behavior of particles and fields at the most fundamental level. Energy, momentum, angular momentum, and other physical quantities are constrained by h, which provides a unifying principle across quantum mechanics. The role of Planck's constant is not limited to theoretical physics. It underpins a vast range of experimental techniques and technologies. For example, spectroscopy relies on the quantization of energy to probe the structure of atoms and molecules. Each spectral line corresponds to a transition between quantized energy levels, and the energy of the photons involved is determined directly by Planck's constant. Without it, the precise prediction and measurement of spectra would be impossible. Similarly, the operation of lasers depends on the stimulated emission of photons with energies defined by h. These practical applications demonstrate that Planck's constant is not an abstract mathematical construct, but a fundamental, measurable property of nature. The constant also plays a central role in defining the behavior of electrons in atoms. Bohr's model of the hydrogen atom demonstrated that electrons occupy discrete orbits, with angular momentum quantized in units of h divided by 2 pi. Transitions between these orbits involve the absorption or emission of photons with energies given by E equals h nu. This quantization explains the discrete spectral lines of hydrogen and other atoms, linking theoretical principles directly to observable phenomena. In modern quantum mechanics, Planck's constant continues to serve as the key parameter in Schrödinger's equation, governing the evolution of wave functions and the probabilistic behavior of particles. Planck's constant also determines the fundamental limits of measurement in the quantum world. Heisenberg's uncertainty principle, one of the cornerstones of quantum mechanics, establishes that certain pairs of physical properties, such as position and momentum, cannot be simultaneously measured with arbitrary precision. The product of the uncertainties is constrained by a factor involving h. This principle has profound implications for both theory and experiment, showing that there is a fundamental limit to knowledge at the quantum scale. Planck's constant, therefore, is not only a measure of energy, but also a measure of the universe's intrinsic indeterminacy. The historical development of our understanding of Planck's constant reveals a remarkable interplay between theory and experiment. Initially introduced to solve the problem of blackbody radiation, it soon found applications across physics, from the photoelectric effect to atomic spectra. Each successive discovery reinforced the centrality of H and demonstrated its universal applicability. The constant emerged not as an isolated number, but as a fundamental principle, guiding the development of quantum mechanics and shaping our understanding of matter, energy, and radiation. The constant also has implications for the philosophical foundations of physics. Its discovery challenged classical notions of continuity and determinism, suggesting that the universe at its most fundamental level is discrete and probabilistic. It raises questions about the nature of reality, the limits of human knowledge, and the relationship between measurement and existence. The universality of H implies that these principles are not local or contingent, but intrinsic to the structure of nature itself. By introducing a scale at which classical concepts fail, Planck's constant forces a re-evaluation of our understanding of the physical world. Technologically, Planck's constant has enabled advances that were unimaginable in Planck's time. Quantum mechanics, with H at its core, underpins semiconductors, integrated circuits, lasers, and magnetic resonance imaging. It allows for precise manipulation of electrons, photons, and atoms, leading to innovations in computing, communication, medicine, and materials science. In emerging fields such as quantum computing, H sets the fundamental limits of information processing, energy transfer, and entanglement. The small numerical value of the constant belies its enormous practical significance. It governs the operation of technologies that define modern civilization. Understanding Planck's constant also illuminates the structure of matter. Electrons, protons, and neutrons obey quantized energy rules, with transitions between levels governed by H. Molecular vibrations, rotational states, and chemical reactions are all quantized in ways that can be predicted and manipulated using the constant. Even phenomena such as superconductivity, superfluidity, and the behavior of Bose-Einstein condensates depend on the principles established by Planck. The constant is the fundamental unit that enables scientists to describe, predict, and control the microscopic world. The constant's role in defining natural units is particularly significant in theoretical physics. By combining h with the speed of light and the gravitational constant, scientists define Planck length, Planck time, Planck mass, and Planck energy. These units represent the smallest scales at which current physical theories are meaningful and provide insight into the earliest moments of the universe. In this way, Planck's constant bridges the microscopic and cosmological realms, linking quantum mechanics with the broader structure of the cosmos. It is both a numerical measure and a conceptual guide, defining the scale at which the deepest laws of nature operate. The universality of Planck's constant underscores the consistency of physical law across space and time. The same constant governs energy transitions in atoms on Earth as it does in distant stars and galaxies. It applies equally to photons traveling billions of light years across the cosmos and to electrons in laboratory experiments. This constancy allows scientists to formulate universal theories, make precise predictions, and extend quantum principles across diverse systems. Planck's constant is not merely a local parameter, but a fundamental measure of the universe itself, linking phenomena from the microscopic to the cosmic. Planck's constant also provides a framework for understanding the limits of classical approximation. At scales much larger than h, energy appears continuous, and classical physics suffices to describe macroscopic behavior. But at scales comparable to h, discrete energy levels, probabilistic outcomes, and quantum interference dominate. This duality explains why classical mechanics works for planets and baseballs, but fails for atoms and photons. Planck's constant defines the boundary between these regimes, a critical scale that determines when quantum effects must be considered. It is the key to understanding why the microscopic and macroscopic worlds follow different rules. Finally, the study of Planck's constant illuminates the profound interplay between theory, observation, and conceptual insight. It began as a solution to a narrow experimental problem, yet its implications extend across all of physics. It bridges classical and quantum worlds, unites matter and radiation, and provides a consistent scale for understanding energy, time, and action. Its discovery exemplifies the power of careful observation, mathematical reasoning, and imaginative thinking to reveal hidden structures in nature. Planck's constant is not just a number. It is a window into the fundamental order of the universe. The experimental confirmation of Planck's constant reinforced its status as a fundamental property of nature. The early measurements of Blackbody radiation, which had inspired its introduction, were soon supplemented by additional precision experiments. Each new dataset confirmed that energy is emitted and absorbed in discrete quanta, with the energy of each quantum given by the product of Planck's constant and the frequency. Techniques such as spectroscopy provided ever more precise measurements, allowing physicists to test the accuracy of quantum predictions to astonishing degrees. These confirmations transformed Planck's constant from a theoretical construct into a measurable, universal quantity, establishing its legitimacy in the scientific community and solidifying its central role in physics. Spectroscopy, in particular, provided compelling evidence of quantization. When atoms and molecules are excited by heat, electricity, or light, they emit radiation at specific frequencies. These spectral lines correspond precisely to transitions between quantized energy levels, with the energy differences determined by h. Early studies of hydrogen and other simple atoms demonstrated that the spectra could be predicted accurately using Planck's constant. As experiments grew more sophisticated, spectroscopic techniques allowed scientists to probe the fine structure of atomic and molecular systems, revealing subtleties such as spin-orbit coupling, hyper-fine splitting, and molecular vibrations, all governed by the principles encapsulated in Planck's constant. In this way, H became a bridge connecting theoretical equations to tangible experimental observations. In the atomic realm, Planck's constant governs the structure and stability of matter. Electrons occupy discrete orbitals within atoms, and transitions between these orbitals involve the emission or absorption of quanta of energy. This discrete arrangement ensures that atoms have defined, stable structures and predictable chemical behavior. Without Planck's constant, electrons would not be confined to stable energy levels, and atoms as we know them could not exist. The constant thus underpins the very architecture of matter, from the simplest hydrogen atom to complex macromolecules, providing the numerical measure that defines the permissible energy states of electrons and the quantized nature of chemical bonds. Planck's constant also plays a pivotal role in the field of condensed matter physics. The behavior of solids, liquids, and gases at the microscopic level depends on quantized energy levels. Vibrations of atoms in a crystal lattice, known as phonons, are quantized, and their energies are multiples of h times the vibrational frequency. This quantization determines the thermal and electrical properties of materials, influencing heat capacity, conductivity, and the behavior of semiconductors. Superconductivity, a phenomenon in which electrons move through a material without resistance, relies on the precise understanding of quantized energy states and interactions mediated by Planck's constant. In these contexts, h is not a distant abstraction, but an operational parameter that guides the design and manipulation of materials with extraordinary properties. The constant also defines the energy of photons, the discrete packets of light that underpin electromagnetic interactions. Each photon carries an energy E equals h nu, where nu is the frequency of the light. This principle governs phenomena ranging from the emission of light by stars to the absorption of photons in photosynthesis. The photoelectric effect, studied by Einstein, demonstrated that light could eject electrons from a metal only if the photon's energy exceeded a threshold value determined by h. This effect confirmed the particle-like behavior of light and reinforced the universality of Planck's constant, linking atomic scale interactions to the macroscopic phenomena of radiation and electricity. Beyond individual particles, Planck's constant governs fundamental physical limits. Heisenberg's uncertainty principle shows that certain pairs of quantities, such as position and momentum, cannot be simultaneously measured with arbitrary precision. The product of these uncertainties is constrained by a factor of h, indicating that indeterminacy is not a limitation of measurement tools but a fundamental feature of nature. This principle applies to all quantum systems, from electrons in atoms to photons in optical experiments, highlighting the deep, pervasive influence of Planck's constant on the structure of reality. It establishes boundaries for knowledge, measurement, and control at the quantum level, emphasizing that h is both a measure of energy and a measure of nature's intrinsic constraints. Technological applications of Planck's constant are both extensive and transformative. Lasers, for instance, operate on the principle of stimulated emission, where electrons transition between discrete energy levels, emitting photons with energies determined by h. Semiconductor devices, which form the foundation of modern electronics, rely on quantized energy bands and electron transitions, again governed by Planck's constant. These devices have enabled the digital revolution, powering computers, telecommunications, medical imaging, and countless other technologies. Even the emerging fields of quantum computing and quantum communication depend critically on h, which defines the minimum action, energy transfer, and information processing limits in quantum systems. The universality of Planck's constant also connects microscopic phenomena to cosmic scales. Light emitted by atoms in distant stars, traveling across billions of light years, obeys the same quantization rules as photons emitted in a laboratory on Earth. This constancy allows astronomers to interpret stellar spectra, identify elemental compositions of distant celestial bodies, and probe the early universe. The same constant governs interactions at the smallest scales and guides observations at the largest scales, unifying physics across immense spans of space and time. In this way, Planck's constant is a bridge between the subatomic and cosmic realms, linking human experiments to the universal order. In the realm of chemical reactions, Planck's constant determines the rates and probabilities of transitions. Molecular vibrations and rotations are quantized, and chemical bonds form and break according to energy differences defined by H. Spectroscopic measurements, infrared absorption, and Raman scattering all rely on the precise quantization introduced by Planck's constant. This knowledge allows chemists to manipulate reactions, design new molecules, and develop advanced materials, illustrating the practical significance of H beyond theoretical physics. Its influence permeates not only the microcosm of atoms and molecules, but also the macroscopic applications that define modern science and technology. Planck's constant also guides the development of quantum field theory and particle physics. In these fields, the interactions of fundamental particles are described by quantum rules, with energies, momenta, and angular momenta quantized according to H. The Standard Model of particle physics incorporates the constant in defining interactions between electrons, quarks, and photons, allowing precise predictions of particle behavior and the outcomes of high-energy collisions. Experiments in particle accelerators, such as those at CERN, measure phenomena that occur on scales where Planck's constant is the defining scale of action. Its presence ensures the consistency and predictability of particle interactions, reinforcing the idea that H is foundational to the structure of matter itself. The philosophical significance of Planck's constant continues to inspire reflection on the nature of reality. By defining the scale at which energy is quantized, it challenges classical notions of smooth, continuous motion and determinism. It introduces the idea that the universe, at its most fundamental level, is discrete and probabilistic. Observations are not passive. The act of measurement interacts with the system, and outcomes are constrained by H. This perspective reshapes our understanding of causality, reality, and knowledge, emphasizing that even the most precise human instruments cannot circumvent the fundamental limits imposed by the quantum structure of nature. Planck's constant also plays a role in defining new standards of measurement. In recent years, it has been used to redefine the kilogram, the unit of mass in the international system of units, by linking mass to fundamental physical constants rather than physical artifacts. By fixing the value of H, the unit of mass is now determined through precise measurements of energy and frequency, reflecting the centrality of Planck's constant in connecting theoretical physics to practical standards. This development exemplifies how a seemingly abstract number governs both the smallest scales of quantum interactions and the practical conventions of human measurement. In experimental physics, Planck's constant underlies precision instruments such as atomic clocks. These clocks measure the frequency of radiation associated with transitions between quantized energy levels in atoms, with the frequency directly related to H. Atomic clocks provide extraordinary accuracy, enabling global positioning systems, telecommunications, and fundamental tests of physical law. Once again, the tiny number introduced to solve a radiation problem proves to have enormous practical significance, governing technologies that shape everyday life and the global infrastructure of modern civilization. Even in the realm of theoretical speculation, Planck's constant provides a foundation. In attempts to unify quantum mechanics and gravity, such as theories of quantum gravity or string theory, H defines the scale at which conventional physical laws must be modified. The Planck length, Planck time, and Planck energy, all derived from H in combination with other fundamental constants, mark the scales where new physics emerges. These considerations suggest that Planck's constant is not merely a feature of atomic and molecular systems, but a window into the deepest structure of spacetime itself. The nature of light has long captivated scientists and philosophers alike, from the earliest musings of the ancients to the sophisticated experiments of modern physics. Light was once considered a continuous wave, an elegant oscillation of electric and magnetic fields propagating through space. This perspective, formalized in Maxwell's equations, successfully explained reflection, refraction, interference, and diffraction. Yet at the turn of the 20th century, a series of perplexing observations challenged this wave, only conception leading to one of the most profound revolutions in physics, the recognition that light, like matter, exhibits quantized behavior governed by Planck's constant. The story begins with the photoelectric effect, a phenomenon in which light striking a metal surface ejects electrons. Classical wave theory predicted that increasing the intensity of light should increase the energy of emitted electrons. Experimentally, however, no such relationship was observed. Instead, electrons were emitted only when the light exceeded a certain threshold frequency, and the energy of the electrons depended on the frequency of the light, not its intensity. These observations could not be reconciled with a purely wave-based model. It was Albert Einstein who, building upon Planck's earlier work on quantized energy, proposed a radical solution. Light itself is composed of discrete packets of energy, later called photons, with each photon carrying an energy proportional to its frequency, E equals h nu. This insight was transformative. It extended the principle of quantization from the absorption and emission of energy by matter to the very medium of light itself. Planck's constant was the proportionality factor, the fundamental measure connecting the frequency of a photon to the energy it carries. The realization that light has both particle-like and wave-like characteristics challenged centuries of classical thought and laid the foundation for the concept of wave-particle duality, a cornerstone of quantum theory. Wave-particle duality revealed that light does not conform to a singular, intuitive model. In some experiments, light behaves like a wave, producing interference and diffraction patterns. In others, it behaves like a particle, transferring discrete packets of energy to electrons and atoms. The energy of these packets is dictated by Planck's constant, establishing a direct, quantitative link between the quantum properties of light and its observable effects. This duality is not merely a philosophical curiosity, but a measurable, predictable aspect of nature, confirmed repeatedly through precise experiments. The implications of this duality extend far beyond the photoelectric effect. Compton scattering, for example, demonstrates that photons collide with electrons much like billiard balls, exchanging energy and momentum in discrete amounts consistent with H. Similarly, the development of quantum optics relies on the quantization of light to describe phenomena such as stimulated emission, photon entanglement, and the behavior of light in cavities and waveguides. In every case, Planck's constant governs the energy carried by photons, defining the scale at which quantum effects become significant and connecting the discrete behavior of light to the broader principles of quantum mechanics. The concept of quantized light also reshaped our understanding of radiation and energy transfer. Blackbody radiation, the original context in which Planck introduced his constant, now found a deeper interpretation. Each atom or molecule in a heated object emits or absorbs radiation in discrete quanta, with energies proportional to the frequency of the radiation. These quanta, or photons, are indivisible and follow statistical distributions that determine the overall spectrum of emitted radiation. By quantizing energy in this way, Planck's constant explains the precise shape of blackbody spectra, resolves the ultraviolet catastrophe, and bridges the gap between macroscopic observations and microscopic quantum behavior. Planck's constant also defines the limits of coherence and interference in light. Experiments with lasers, interferometers, and optical cavities reveal that the behavior of light depends critically on the quantization of energy. Coherent light, as in a laser, consists of photons that share the same phase and frequency, producing highly controlled interference patterns. The energy of each photon, determined by h, sets the fundamental scale for interactions, dictating the intensity, color, and efficiency of emission. In this way, Planck's constant links the discrete quantum world to the continuous wave, like phenomena observed in optical systems, uniting particle and wave descriptions under a single quantitative framework. The dual nature of light also has profound implications for our understanding of measurement and observation. In the double-slit experiment, individual photons passing through slits produce an interference pattern over time, as though each photon interferes with itself as a wave. Yet the detection of each photon is a discrete event, revealing the particle-like aspect. Planck's constant underpins the energy of each photon, defining the scale of quantization and ensuring that the probabilistic outcomes of measurement remain consistent with the conservation of energy. The experiment exemplifies the subtle interplay between wave and particle properties, with h serving as the numerical constant that bridges these two complementary aspects of reality. The role of Planck's constant in light extends to atomic and molecular interactions. Absorption and emission spectra depend on the quantization of photon energy. When electrons transition between discrete energy levels in an atom, they absorb or emit photons with energies precisely equal to the difference between the levels, multiplied by h. This principle explains the discrete spectral lines observed in atomic spectra and allows for precise determination of atomic structure, chemical composition, and molecular dynamics. It also underpins a wide range of technologies, from spectroscopy and lasers to solar cells and photodetectors, demonstrating that the abstract constant h has direct, measurable consequences in both scientific and technological contexts. The quantum nature of light also plays a central role in modern communication technologies. Fiber optic systems, laser-based data transmission, and quantum key distribution all rely on the discrete, quantized behavior of photons. The energy of each photon, determined by Planck's constant, governs the interactions with detectors, the absorption and emission processes in materials, and the coherence properties essential for long-distance communication. Without h, the fundamental principles of these technologies would be undefined, illustrating the profound impact of this single constant on contemporary life and global infrastructure. Moreover, Planck's constant informs our understanding of fundamental physical limits. The minimum energy of a photon for a given frequency is fixed by h, setting boundaries for processes such as photoelectric emission, photon, induced chemical reactions, and energy transfer in biological systems. The quantization also implies that energy cannot be subdivided indefinitely, establishing discrete thresholds that define atomic stability, chemical bonding, and molecular behavior. In this way, H governs not only the abstract realm of quantum theory, but also the tangible properties of matter and light in the natural world. The universality of Planck's constant in light phenomena is striking. The same constant governs the emission of photons in a laboratory experiment, the radiation from the sun, and the distant starlight observed in galaxies billions of light years away. This invariance allows scientists to extend quantum principles to the largest scales, connecting laboratory physics to astrophysics and cosmology. Photons traveling across the cosmos obey the same quantization rules as those generated in human-made lasers, ensuring that fundamental physical laws remain consistent across space and time. Planck's constant is thus a bridge linking the microscopic world of quanta to the macroscopic universe. In addition to its role in energy quantization, H also sets the scale for momentum and angular momentum in photons. A photon of light carries momentum p equals E/c, where E equals h nu, and can exert pressure on surfaces, as demonstrated in the phenomenon of radiation pressure. This principle has practical applications ranging from solar sails for space propulsion to optical tweezers that manipulate microscopic particles. In each case, the energy and momentum of the photon are quantized according to Planck's constant, highlighting its role as a fundamental measure of the physical properties of light. Planck's constant further governs the interaction of light with matter at the quantum level. In absorption processes, a photon with energy E equals h, you can excite an electron to a higher energy level, provided the energy matches the difference between levels. Emission processes, including spontaneous and stimulated emission, also rely on this quantization. Lasers, masers, and LED all operate by exploiting these transitions, demonstrating that the principles first introduced to resolve Blackbody radiation are now central to countless technological applications. Planck's constant is the numerical key that ensures energy is transferred in discrete, predictable amounts, enabling the precise control necessary for modern optics and photonics. The wave-particle duality of light, quantified by Planck's constant, also illuminates deeper theoretical principles. In quantum electrodynamics, light is treated as both a wave and a particle, with photons mediating electromagnetic interactions. The interactions of photons with charged particles, the probabilities of scattering events, and the quantization of the electromagnetic field all depend on H. The constant provides the numerical measure that reconciles the seemingly contradictory behaviors of waves and particles, allowing physicists to predict experimental outcomes with extraordinary precision. Without this fundamental constant, the unification of wave and particle descriptions would be impossible. Even at the cosmological scale, Planck's constant remains central. The cosmic microwave background radiation, the afterglow of the Big Bang, exhibits a spectrum that can be precisely described using quantized photons and Planck's law. The energy, frequency, and distribution of these primordial photons are determined by H, connecting the behavior of light observed across the universe to the same fundamental principles discovered in early 20th century laboratories. This universality reinforces the idea that Planck's constant is not a local curiosity but a fundamental property of nature, governing interactions from the smallest particles to the vast expanses of space. The exploration of light through the lens of Planck's constant also reshapes our understanding of measurement and observation in physics. Each photon detected represents a discrete quantum of energy, and the statistical distribution of photons determines the observable intensity and spectrum. Quantum optics, photon counting experiments, and single photon interference studies all rely on the precise quantization defined by h. In these experiments, the constant dictates the resolution, precision, and limits of measurement, revealing the fundamental interplay between observation, energy, and probability at the quantum scale. Finally, the study of Planck's constant and light underscores the broader significance of quantization in the universe. Light, once understood as a continuous wave, is now recognized as composed of discrete quanta governed by h. This realization links the behavior of photons to that of electrons, atoms, and molecules, establishing a unified framework for understanding matter and energy. Planck's constant is the numerical anchor for these principles, ensuring that the energy of quanta, the scale of interactions, and the limits of measurement remain consistent across all phenomena. It is both a theoretical cornerstone and a practical tool, shaping our understanding of light, matter, and the universe itself. As the implications of quantized light unfolded, scientists realized that Planck's constant was not merely a parameter in an equation, but a deep statement about how nature permits energy to exist and interact. The discrete nature of photons transformed the way physicists thought about causality, determinism, and even reality itself. Light, once assumed to be a smooth and continuous entity, was revealed to arrive in indivisible units, each governed by the same universal constant. This realization forced a radical rethinking of how information, energy, and interaction propagate through space. One of the most striking consequences of this discovery emerged in the development of quantum optics, a field that treats light as a collection of quantized particles while still preserving its wave-like behavior. In this framework, electromagnetic radiation is described as a quantized field, with photons acting as excitations of that field. Planck's constant determines the size of each excitation, setting the scale at which fluctuations become meaningful. Vacuum itself, once thought to be empty, is now understood as a dynamic arena filled with temporary photon fluctuations, all constrained by h. These vacuum fluctuations influence atomic stability, spontaneous emission, and even the forces between neutral objects, such as the Casimir effect. The Casimir effect, predicted in the mid-20th century and later experimentally confirmed, provides a vivid demonstration of how Planck's constant governs the quantum nature of light even in empty space. Two uncharged metal plates placed extremely close together experience an attractive force due to the restriction of allowed electromagnetic modes between them. This force arises from the quantization of the electromagnetic field, with Planck's constant determining the energy of each allowed mode. The effect is small but measurable, offering direct evidence that the quantum behavior of light is not limited to energetic photons, but permeates the very fabric of space itself. Planck's constant also plays a defining role in spontaneous emission, a process that classical physics could not adequately explain. An excited atom will eventually emit a photon and transition to a lower energy state, even in complete darkness. This emission is not triggered by an external disturbance, but by interactions with the quantized electromagnetic field. The probability and energy of the emitted photon are dictated by h, reinforcing the idea that light and matter are inseparably linked through quantization. Without Planck's constant, spontaneous emission would be an inexplicable phenomenon, defying both classical intuition and experimental observation. The development of lasers further cemented the central role of quantized light. Laser operation depends on stimulated emission, a process in which an incoming photon induces an excited atom to emit a second photon with identical energy, frequency, phase, and direction. The precision of this process relies entirely on the discrete energy levels of atoms and the quantized energy of photons, both governed by Planck's constant. The resulting beam of coherent light is one of the most striking manifestations of quantum principles at a macroscopic scale. From medical surgery to telecommunications and scientific instrumentation, lasers demonstrate how a constant discovered to solve an abstract theoretical problem became the backbone of modern technology. As photon-based technologies advanced, scientists began to manipulate individual photons with extraordinary precision. Single photon sources, detectors, and interferometers made it possible to study light at its most fundamental level. Experiments showed that even when photons are sent one at a time through an interferometer, they still produce interference patterns over time. Each photon behaves as if it explores multiple paths simultaneously, a behavior that defies classical logic yet remains perfectly consistent with quantum theory. Planck's constant ensures that each detection event corresponds to a fixed quantum of energy, preserving energy conservation while allowing probabilistic outcomes. This probabilistic nature of photon behavior reshaped the philosophy of physics. The classical world, you assumed that if the present state of a system were known with sufficient precision, its future could be predicted exactly. Quantum mechanics shattered this assumption. While Planck's constant does not introduce randomness by itself, it sets the scale at which uncertainty becomes unavoidable. The energy-time uncertainty principle, closely tied to H, implies that the precise timing and energy of photon emission cannot both be known with infinite accuracy. This uncertainty is not a limitation of measurement devices, but a fundamental feature of reality. The role of Planck's constant in uncertainty becomes especially clear in high-frequency light, such as X-rays and gamma rays. As frequency increases, the energy of each photon increases proportionally, making quantum effects impossible to ignore. High-energy photons can ionize atoms, break chemical bonds, and alter biological structures, all because their energy comes in discrete packets fixed by H. These interactions highlight the profound connection between light and matter, showing how the quantization of energy governs processes ranging from chemical reactions to radiation damage and medical imaging. Planck's constant also defines the threshold between classical and quantum descriptions of light. At low frequencies or high intensities, the collective behavior of many photons can often be approximated as a classical wave. However, when dealing with individual photons or low-intensity fields, the quantum nature becomes dominant. This transition is not abrupt but gradual, with H acting as the scale factor that determines when quantum effects become noticeable. The constant thus serves as a bridge between two seemingly incompatible descriptions of nature, unifying them within a single theoretical framework. In astrophysics, the quantization of light provides essential insights into the universe. The light emitted by stars, galaxies, and cosmic events carries information encoded in individual photons. Spectral lines reveal the composition, temperature, and motion of distant objects, all through the quantized interaction between photons and atoms. Planck's constant ensures that these interactions are precise and universal, allowing scientists to interpret cosmic light using the same principles established in laboratory experiments. Whether observing a nearby atom or a distant quasar, the same quantum rules apply. The cosmic microwave background radiation offers one of the most powerful confirmations of this universality. This ancient light, emitted when the universe was only a few 100,000 years old, follows a nearly perfect blackbody spectrum. The distribution of photon energies in this radiation is described exactly by Planck's law, with h setting the scale of energy quantization. The remarkable agreement between theory and observation underscores the enduring relevance of Planck's constant, linking the earliest moments of the cosmos to modern quantum theory. As quantum theory matured, the quantization of light became central to the development of quantum electrodynamics, one of the most successful theories in the history of science. This theory describes the interactions between light and charged particles with extraordinary accuracy, predicting experimental results to many decimal places. Planck's constant appears throughout its equations, governing the strength of interactions, the probability of processes, and the structure of the electromagnetic field. Its presence is not optional or adjustable. It is fundamental, woven into the very fabric of the theory. Beyond physics, the implications of quantized light have reached into chemistry and biology. Photosynthesis, for example, depends on the absorption of individual photons by pigment molecules. Each absorbed photon triggers a chain of chemical reactions that convert light energy into chemical energy. The efficiency and dynamics of this process are governed by the discrete energy of photons, determined by Planck's constant. Even vision relies on the detection of single photons by photoreceptor cells in the retina, demonstrating that the quantum nature of light plays a direct role in human perception. The emergence of quantum information science has further elevated the importance of photons. Photons are ideal carriers of quantum information because they interact weakly with their environment and can travel long distances without significant loss. Quantum communication, quantum cryptography, and emerging quantum networks all rely on the controlled generation, manipulation, and detection of individual photons. In these technologies, Planck's constant defines the fundamental unit of energy and action, ensuring that information is encoded and transmitted in discrete, quantized forms. Quantum entanglement, one of the most counterintuitive features of quantum theory, also finds expression in photon behavior. Pairs of entangled photons exhibit correlations that cannot be explained by classical physics, regardless of the distance separating them. These correlations do not transmit energy or information faster than light, but they reveal a deep non-local structure underlying quantum reality. The creation and measurement of entangled photons depend on the quantization of light, with H governing the energy and phase relationships that make entanglement possible. The philosophical implications of these discoveries are profound. Light, once a symbol of clarity and continuity, now embodies uncertainty and discreteness. Planck's constant reveals that nature operates in steps rather than smooth gradients, challenging our intuitive understanding of causality and continuity. The universe, at its most fundamental level, is not infinitely divisible but structured around finite units of action. This insight reshapes our conception of reality, suggesting that the fabric of existence is woven from discrete threads rather than continuous cloth. Planck himself was initially uneasy with the implications of his discovery. He viewed the constant as a mathematical convenience rather than a statement about the nature of reality. Yet, as evidence accumulated, it became clear that H was not a temporary fix, but a fundamental constant of nature. Its presence in every quantum description of light confirmed that energy quantization was not an artifact of theory, but an intrinsic feature of the universe. Today, Planck's constant stands alongside the speed of light and the gravitational constant as one of the pillars of physical law. It defines the scale at which classical concepts break down and quantum behavior emerges. In the realm of light, it determines the energy of photons, the limits of measurement, and the nature of interaction. From the glow of a distant star to the pulse of a laser, from the warmth of sunlight to the subtle processes within living cells, the influence of H is everywhere. Ultimately, the quantization of light reveals a universe that is both elegant and mysterious. Planck's constant provides the numerical key that unlocks this mystery, translating abstract frequencies into tangible energies and connecting wave-like phenomena to particle-like events. It is the constant that allows light to be both wave and particle, continuous and discrete, deterministic and probabilistic. Through it, the universe speaks in quanta, and light becomes not just illumination, but a messenger of the deepest laws of nature. As Planck's constant became firmly embedded in the description of light and radiation, its influence expanded far beyond photons and optical phenomena. What initially appeared to be a correction for an obscure thermal problem soon revealed itself as a universal constant governing the behavior of all physical systems at the smallest scales. Nowhere is this more evident than in the everyday machinery of quantum physics itself, where Planck's constant quietly dictates how particles move, how systems evolve over time, and how reality reveals itself through measurement. At the heart of this transformation lies the realization that energy, momentum, and even action itself are quantized. Planck's constant is not simply a number that appears in equations. It defines the scale at which classical intuition fails and quantum behavior takes over. In classical mechanics, objects have well-defined positions and velocities, and their motion can be predicted precisely if initial conditions are known. Quantum mechanics, however, introduces a fundamentally different framework. The moment Planck's constant enters the picture, certainty gives way to probability, and trajectories are replaced by wave functions. The Schrödinger equation, the central equation of non-relativistic quantum mechanics, places Planck's constant at its core. This equation describes how the quantum state of a system evolves over time, and the presence of H determines how rapidly and in what manner that evolution occurs. The wave function itself has no classical counterpart. It does not describe a particle's exact position or velocity, but rather encodes probabilities. Planck's constant controls the spread of these probabilities, determining how sharply or diffusely a particle's behavior can be defined. When Planck's constant is mathematically allowed to shrink towards zero, the Schrödinger equation smoothly transforms into classical mechanics. This limit shows that classical physics is not wrong but incomplete, emerging naturally when quantum effects become negligible. The existence of this limit highlights the role of Planck's constant as a boundary marker between two worlds. It is the numerical reason why planets follow predictable orbits while electrons do not, why baseballs behave classically while atoms demand a quantum description. Momentum, once thought of as a purely mechanical quantity, is also reshaped by Planck's constant. In quantum mechanics, momentum is associated with wave-like properties, specifically wavelength. The de Broglie relation shows that every particle has an associated wavelength inversely proportional to its momentum, with Planck's constant as the proportionality factor. This insight revealed that wave-particle duality is not unique to light, but applies universally to matter. Electrons, protons, atoms, and even complex molecules exhibit wave-like behavior under the right conditions, all because Planck's constant allows momentum to be translated into wavelength. This wave nature of matter has direct, observable consequences. Electron diffraction experiments demonstrate that electrons passing through a crystal form interference patterns similar to those produced by light waves. These patterns can only be explained if electrons possess wavelengths determined by h. The same principle governs scanning tunneling microscopes, which rely on quantum tunneling to image surfaces at atomic resolution. Tunneling, a phenomenon impossible in classical physics, occurs because particles described by wave functions can penetrate energy barriers, with Planck's constant setting the scale for how likely this penetration is. The uncertainty principle provides one of the most famous and misunderstood expressions of Planck's constant. It states that certain pairs of physical quantities, such as position and momentum, cannot both be known with arbitrary precision. The product of their uncertainties is bounded by a value proportional to h. This is not a statement about experimental limitations or technological shortcomings. It is a fundamental feature of nature. The presence of Planck's constant ensures that the universe itself does not allow perfect precision at the quantum level. This uncertainty has profound practical consequences. It prevents electrons from collapsing into atomic nuclei, ensuring the stability of atoms. If electrons could have both precisely defined positions and momenta, classical electrodynamics predicts they would radiate energy continuously and spiral into the nucleus. Quantum uncertainty, enforced by Planck's constant, prevents this collapse by imposing a minimum spread in position and momentum. In this sense, the very existence of matter in its familiar form depends on h. Energy quantization in bound systems offers another illustration of Planck's constant at work. In atoms, electrons can occupy only specific energy levels, and transitions between these levels involve the absorption or emission of energy in discrete amounts. These energy differences are proportional to Planck's constant linking atomic structure directly to quantum action. The resulting spectral lines are fingerprints of elements, allowing scientists to identify substances across vast distances. This is not an exotic effect confined to laboratories. It is the reason astronomers can determine the composition of stars and galaxies by analyzing their light. In solids, Planck's constant governs the behavior of electrons in crystal lattices, giving rise to band structures that determine whether a material behaves as a conductor, insulator, or semiconductor. The modern electronics industry rests entirely on this quantum foundation. Transistors, integrated circuits, and microprocessors all depend on the controlled movement of electrons through energy bands defined by quantum mechanics. The size, speed, and efficiency of electronic devices are ultimately constrained by Planck's constant, which sets limits on how small components can be made before quantum effects dominate. Thermal physics, too, bears the imprint of Planck's constant. At low temperatures, classical predictions fail dramatically, and quantum effects become dominant. The specific heat of solids, for example, deviates from classical expectations as temperature decreases. Quantum theory, incorporating energy quantization governed by h, accurately explains these deviations. Phenomena such as superconductivity and superfluidity emerge only when quantum effects extend to macroscopic scales, again highlighting how Planck's constant controls the transition between classical and quantum regimes. superconductivity provides a particularly striking example of quantum behavior in everyday materials. In a superconducting state, electrons form pairs that move coherently through a lattice without resistance. This collective quantum state is described by a single wave function, whose properties are determined by Planck's constant. Magnetic flux in superconductors is quantized, appearing only in discrete units proportional to h. These effects are not theoretical curiosities, but have practical applications in medical imaging, particle accelerators, and energy-efficient power systems. Time itself takes on a new character under the influence of Planck's constant. The energy-time uncertainty relation implies that processes occurring over very short timescales involve inherent energy uncertainty. This principle explains the natural line width of spectral lines and the finite lifetimes of excited states. It also plays a role in virtual particle processes, where energy conservation appears to be temporarily violated within limits allowed by quantum uncertainty. Planck's constant defines these limits, ensuring consistency while allowing rich and complex behavior. Measurement, a concept taken for granted in classical physics, becomes deeply intertwined with Planck's constant in quantum mechanics. Any attempt to measure a quantum system involves an exchange of energy and momentum, and the minimum amount of disturbance is governed by h. This means that observation is not passive. It actively influences the system being observed. The quantization of action ensures that measurements occur in discrete steps rather than smooth continua, shaping the outcomes and probabilities of experimental results. The influence of Planck's constant extends into statistical mechanics, where it determines the density of quantum states available to a system. This affects the behavior of gases, plasmas, and condensed matter systems alike. Quantum statistics, including Fermi, Dirac, and Bose-Einstein distributions, arise because particles are indistinguishable and their states are quantized. These distributions explain the behavior of electrons in metals, the structure of neutron stars, and the formation of Bose-Einstein condensates, all through principles rooted in h. Even chemistry, often viewed as a distinct discipline, is fundamentally shaped by Planck's constant. Chemical bonds arise from the quantum behavior of electrons in molecules. The shapes of molecular orbitals, the energies of bonds, and the rates of chemical reactions are determined by wave functions governed by h. Reaction barriers, tunneling effects, and vibrational modes all depend on quantized energy levels. Without Planck's constant, the rich diversity of chemical behavior that underpins biology and technology would not exist. On a more familiar scale, the warmth you feel from sunlight, the glow of a light bulb, and the operation of digital screens all rely on quantum processes controlled by Planck's constant. Thermal radiation follows Planck's law. Electronic displays depend on quantized energy transitions, and sensors detect discrete energy packets. These are not abstract consequences of an esoteric theory. They are direct manifestations of a constant that quietly governs everyday experience. What makes Planck's constant especially remarkable is its universality. It appears in equations describing electrons in atoms, photons in cavities, phonons in solids, and fields in empty space. It does not depend on the type of particle, the environment, or the scale of observation. Whether describing a single atom or a macroscopic quantum system, the same constant applies. This universality suggests that Planck's constant is not an incidental feature of our theories, but a fundamental property of nature itself. As physics progressed, Planck's constant became so central that it was eventually used to redefine measurement standards. In modern metrology, the kilogram is defined in terms of Planck's constant, linking mass to fundamental quantum principles. This shift reflects a deep philosophical change. Instead of basing units on physical artifacts, science now anchors measurement in immutable constants of nature. Planck's constant, once introduced as a mathematical trick, now underpins the very definition of physical reality. In everyday physics, Planck's constant acts as a silent regulator. It determines when quantum effects can be ignored and when they cannot, shaping the behavior of systems across disciplines. It explains why the macroscopic world appears stable and predictable, while the microscopic world remains probabilistic and strange. It ensures atomic stability, enables modern technology, and connects abstract theory to tangible experience. By embedding itself into the equations that describe motion, energy, measurement, and interaction, Planck's constant transformed physics from a deterministic narrative into a probabilistic one. Yet it did so without introducing chaos. Instead, it imposed a new kind of order, one governed by statistical laws and quantized action. The universe did not become less understandable. It became deeper, richer, and more subtle. This quiet constant, small in numerical value, yet vast in implication, governs the rhythm of the quantum world. Every vibration of an atom, every transition of an electron, and every quantum leap of energy unfolds in steps measured by Planck's constant. In this way, the ordinary workings of the physical world are inseparably tied to a discovery that began as an attempt to explain an anomaly and ended by redefining reality itself. As quantum mechanics matured, the presence of Planck's constant became so deeply ingrained that it began to redefine what physicists meant by physical reality. Rather than describing objects with precise trajectories and definite properties, the quantum framework revealed a world governed by probabilities, amplitudes, and constraints set by a universal scale of action. Planck's constant defines that scale. It determines how sharply reality can be defined and how finely nature allows us to divide physical processes. One of the most subtle yet powerful roles of Planck's constant lies in the concept of action itself. In classical mechanics, action is a mathematical quantity derived from energy and time, used to determine the path a system follows. In quantum mechanics, action becomes quantized. Physical systems no longer explore just one path, but all possible paths simultaneously, with each path contributing to the outcome. The contribution of each path is weighted by an exponential factor involving Planck's constant. When the action of a path is much larger than h, destructive interference eliminates most possibilities, and classical behavior emerges. When the action is comparable to h, multiple paths contribute significantly, and quantum behavior dominates. This insight explains why macroscopic objects follow classical laws, while microscopic systems do not. This path-based view of quantum mechanics reveals Planck's constant as the measure of nature's tolerance for ambiguity. It defines how much deviation from a classical path is allowed before interference suppresses it. The smaller the action relative to h, the more freedom the system has to explore non-classical behavior. In this sense, Planck's constant is not merely a scale, but a regulator of possibility, determining how flexible or constrained reality can be at a given scale. The quantization of angular momentum provides another vivid example of this regulation. In atomic systems, electrons cannot possess arbitrary angular momentum. Instead, Angular momentum comes in discrete units proportional to Planck's constant. This restriction shapes the structure of atoms, the orientation of orbitals, and the magnetic properties of materials. The quantized nature of angular momentum explains why atoms exhibit specific spectral patterns and why magnetic moments align in discrete ways. Without Planck's constant enforcing these limits, atomic structure would be unstable, and the periodic table itself would lose meaning. Spin, an intrinsic form of angular momentum with no classical analog, further underscores the foundational role of Planck's constant. Particles such as electrons possess spin values fixed in units of h, giving rise to fundamental properties like magnetism and the Pauli exclusion principle. This principle, which prevents identical fermions from occupying the same quantum state, is directly responsible for the structure of atoms, the rigidity of matter, and the diversity of chemical behavior. The solidity of the objects around us, from tables to planets, can be traced back to quantum rules enforced by Planck's constant. In quantum dynamics, Planck's constant also governs transition rates and probabilities. The likelihood that a system will move from one state to another depends on matrix elements containing H. These probabilities determine reaction rates, decay processes, and absorption efficiencies across physics and chemistry. Nuclear decay, for example, involves quantum tunneling through energy barriers that would be insurmountable classically. The tunneling probability depends sensitively on Planck's constant, influencing half-lives that range from fractions of a second to billions of years. The stability of matter over cosmic timescales is therefore intimately tied to the numerical value of h. At extremely low temperatures, Planck's constant becomes impossible to ignore even on macroscopic scales. Systems enter regimes where quantum coherence extends over large distances, producing phenomena such as Bose-Einstein condensation. In these states, particles occupy the same quantum state and behave as a single coherent entity. The wavelength associated with each particle, determined by Planck's constant, becomes comparable to the distance between particles, allowing their wave functions to overlap. The resulting collective behavior challenges classical intuition, revealing a form of matter governed directly by quantum rules. These macroscopic quantum states are not mere laboratory curiosities. They offer insight into astrophysical objects such as neutron stars, where extreme densities and low effective temperatures force matter into quantum, degenerate states. The pressure that prevents such stars from collapsing arises not from thermal motion, but from quantum principles linked to Planck's constant. Degeneracy pressure, enforced by the exclusion principle, counteracts gravity and stabilizes these dense remnants. Once again, a constant born in a study of radiation governs the fate of stars. In quantum field theory, Planck's constant plays an even deeper role. Fields are quantized, meaning that each mode of a field behaves like a quantum harmonic oscillator with discrete energy levels separated by amounts proportional to h. Particles emerge as excitations of these fields, blurring the distinction between matter and energy. Creation and annihilation processes occur in discrete steps, with Planck's constant setting the scale for all interactions. The vacuum itself becomes a dynamic entity, filled with fluctuations constrained by h. These vacuum fluctuations have measurable consequences. They contribute to observable shifts in atomic energy levels and influence particle interactions at the smallest scales. Even the stability of the vacuum depends on the balance between quantum fluctuations and fundamental forces, all governed by Planck's constant. The realization that empty space is structured by quantized activity represents one of the most profound shifts in scientific understanding. As experiments grew more precise, Planck's constant became central to defining the limits of measurement. Quantum metrology exploits entanglement and quantum coherence to achieve sensitivities beyond classical limits. The ultimate precision of such measurements is bounded by quantum uncertainty relations involving h. These limits are not technological barriers, but fundamental constraints imposed by nature. Even with perfect instruments, certain quantities cannot be measured more accurately than allowed by Planck's constant. This realization transformed the philosophy of science. Measurement was no longer seen as a passive recording of pre-existing properties, but as an interaction governed by quantum rules. Observables take on definite values only through measurement processes that involve energy exchange quantized by h. The act of observation becomes inseparable from the phenomena being observed, challenging classical notions of objectivity and realism. The universality of Planck's constant also suggests a deep unity among physical laws. Whether describing the vibration of a molecule, the propagation of light, the motion of electrons, or the evolution of quantum fields, the same constant appears. This consistency hints at an underlying simplicity beneath the apparent complexity of nature. Rather than being governed by countless unrelated rules, the universe seems to operate according to a small set of fundamental principles, with Planck's constant acting as one of their central pillars. In modern physics, Planck's constant even shapes our understanding of space and time themselves. At extremely small scales, comparable to the so-called Planck length and Planck time, quantum fluctuations of spacetime are expected to become significant. Although a complete theory of quantum gravity remains elusive, Planck's constant is a key ingredient in all candidate theories. It signals the breakdown of classical geometry and suggests that space and time may themselves be quantized. This possibility represents the frontier of contemporary physics. Just as Planck's original constant revealed the quantization of energy, future discoveries may reveal the quantization of spacetime. If so, Planck's constant will once again stand at the center of a conceptual revolution, linking the smallest scales of reality to the structure of the cosmos. Despite its abstract nature, the influence of Planck's constant is deeply practical. It determines the operating principles of atomic clocks, which define time with extraordinary precision. These clocks rely on quantum transitions whose frequencies are fixed by h. Global positioning systems, telecommunications, and financial networks all depend on this precision. The constant thus shapes not only our understanding of the universe, but the functioning of modern civilization. In redefining measurement standards, Planck's constant has become a bridge between theory and practice. By fixing its value exactly, scientists have anchored units of mass, energy, and time to immutable features of nature. This shift reflects a profound confidence in the universality and permanence of quantum principles. What began as a speculative idea has become the foundation of how humanity measures reality itself. Perhaps the most remarkable aspect of Planck's constant is how quietly it governs so much. It does not announce itself through dramatic forces or obvious effects at human scales. Instead, it works subtly, shaping probabilities, enforcing limits, and ensuring consistency across physical laws. Its influence is felt not through brute strength, but through constraint, defining what is allowed and what is forbidden. Through Planck's constant, the universe reveals a preference for structure over chaos, discreteness over continuity, and probability over certainty. These preferences do not diminish the elegance of nature, they enhance it. The quantum world, though counterintuitive, is governed by precise mathematical relationships, with Planck's constant as their common thread. From the stability of atoms to the coherence of quantum states, from the behavior of electrons to the limits of measurement, Planck's constant defines the grammar of the quantum language. It tells the universe how to count, how to transition, and how to evolve. Without it, the equations of modern physics would lose meaning, and the ordered complexity of the natural world would dissolve. In this way, Planck's constant stands not merely as a number, but as a principle. It encodes the idea that nature operates in finite steps, that action comes in indivisible units, and that reality has a fundamental grain. This insight reshaped physics, transformed technology, and altered humanity's understanding of existence itself. What began as a modest adjustment to a radiation formula ultimately became a revelation about the structure of reality. Planck's constant is the quiet architect of the quantum world, guiding the behavior of matter and energy with unwavering consistency. Its influence is everywhere, from the smallest fluctuations of the vacuum to the largest structures supported by quantum principles. In the rhythm of the universe, Planck's constant sets the beat, ensuring that every quantum step follows a deeper, universal order. As Planck's constant moved from theoretical physics into the applied sciences, its influence quietly began reshaping the technological landscape of the modern world. What once existed only as an abstract proportionality factor in a radiation formula became the invisible foundation of devices, systems, and infrastructures that define contemporary life. The quantum principles governed by Planck's constant are not confined to laboratories or chalkboards. They operate continuously within smartphones, computers, medical equipment, satellites, and communication networks across the globe. At the heart of this technological transformation lies the quantum behavior of electrons in materials. In classical physics, electrons were imagined as tiny charged particles moving freely through conductors. Quantum mechanics revealed a far richer picture. Electrons occupy quantized energy states within atoms and solids, and their behavior is governed by wave functions whose properties are set by Planck's constant. This understanding made it possible to engineer materials with precise electrical properties, giving rise to the semiconductor revolution. Semiconductors depend fundamentally on the existence of energy bands and band gaps, features that emerge from quantum mechanics. Electrons in a crystal lattice can occupy only specific ranges of energy, and transitions between these ranges involve discrete amounts of energy determined by h. By carefully controlling the composition and structure of materials such as silicon, engineers learned to manipulate electron flow with extraordinary precision. Transistors, the basic building blocks of modern electronics, rely entirely on this quantum control. Without Planck's constant governing electron energy levels, the distinction between conductors, insulators, and semiconductors would collapse, and the digital age would never have emerged. As transistors became smaller and more numerous, quantum effects grew increasingly important. At nanometer scales, electrons exhibit tunneling behavior, passing through barriers that would be impenetrable according to classical physics. This tunneling is a direct consequence of wave-particle duality, with Planck's constant determining the probability of such events. Modern microprocessors operate at scales where quantum effects are no longer negligible but actively exploited and managed. The remarkable speed and efficiency of today's computing devices are therefore rooted in principles first revealed through Planck's constant. Optoelectronic technologies provide another vivid demonstration of quantized energy at work. Light-emitting diodes, lasers, and photodetectors all rely on electronic transitions between discrete energy levels. When an electron falls from a higher energy state to a lower one, it emits a photon whose energy is precisely determined by the energy difference, linked directly to Planck's constant. The color of an LED, the wavelength of a laser, and the sensitivity of a detector are all controlled through this relationship. From digital displays to barcode scanners and fiber optic communication, quantized light enables precise and reliable control over electromagnetic radiation. Laser technology, in particular, stands as one of the most powerful technological outcomes of quantum physics. Lasers produce coherent, monochromatic light by exploiting stimulated emission, a process governed entirely by quantized energy transitions. Each photon produced has an energy fixed by h, ensuring uniformity and coherence across the beam. This precision allows lasers to cut metals, perform delicate eye surgeries, transmit data across continents, and probe the structure of matter at atomic scales. The laser's versatility stems directly from the predictability and stability imposed by Planck's constant. Communication technologies have been profoundly shaped by these quantum principles. Fiber optic networks transmit information using photons whose energies and frequencies are precisely controlled. The reliability of these systems depends on the quantized interaction between light and matter, ensuring minimal loss and distortion over long distances. Planck's constant governs the absorption and emission processes within optical fibers and amplifiers, making global high-speed communication possible. The Internet itself, often viewed as a purely digital or software-based phenomenon, rests on a quantum foundation. Medical technology offers some of the most tangible examples of Planck's constant improving human life. Imaging techniques such as X-ray radiography, computed tomography, and positron emission tomography rely on quantized interactions between radiation and matter. X-ray photons carry energies determined by h that allow them to penetrate tissues and reveal internal structures. In nuclear medicine, radioactive tracers emit photons through quantum transitions, enabling precise imaging of metabolic processes. These applications depend on the predictable energy of radiation quanta, ensuring both effectiveness and safety. Magnetic resonance imaging represents another triumph of quantum technology. MRI exploits the quantized spin states of atomic nuclei in a magnetic field. Transitions between these states involve energy differences governed by Planck's constant. By manipulating these transitions with radio frequency pulses, MRI systems produce detailed images of soft tissues without ionizing radiation. The clarity and diagnostic power of MRI arise from the precise control of quantum states, demonstrating how abstract quantum principles translate into life-saving tools. Timekeeping, one of the oldest technological pursuits, has reached unprecedented precision through quantum mechanics. Atomic clocks measure time by tracking transitions between quantized energy levels in atoms such as cesium or rubidium. The frequency of these transitions is fixed by Planck's constant, providing an extraordinarily stable reference. Modern definitions of the second are based on these quantum transitions, enabling navigation systems, scientific experiments, and financial networks to operate with remarkable synchronization. The global positioning system, for example, would be impossible without clocks whose accuracy depends on h. Energy technologies have also been transformed by quantum understanding. Solar cells convert sunlight into electricity through the absorption of photons and the excitation of electrons across a band gap. The efficiency of this process depends on matching photon energies, determined by Planck's constant, to material properties. Advances in photovoltaic technology rely on quantum engineering to minimize energy loss and maximize conversion efficiency. In this way, Planck's constant plays a role in humanity's efforts to harness renewable energy and address global challenges. At smaller scales, quantum sensors exploit the sensitivity of quantum states to external influences. Devices such as superconducting quantum interference devices can detect extremely weak magnetic fields, using quantum coherence and interference effects governed by H. These sensors are used in geology, medicine, and fundamental physics research, demonstrating how quantum effects enable measurements far beyond classical limits. The ability to detect subtle signals rests on the quantized nature of action and energy. The rise of nanotechnology further illustrates the technological reach of Planck's constant. At nanometer dimensions, materials exhibit properties that differ dramatically from their bulk behavior. Quantum confinement alters energy levels, optical properties, and electrical conductivity. Engineers design nanoparticles, quantum dots, and nanowires by exploiting these effects, creating materials with tailored characteristics. Quantum dots, for instance, emit light at specific wavelengths depending on their size, a direct consequence of energy quantization governed by H. These materials are now used in displays, biomedical imaging, and advanced sensors. As computing technology approaches physical limits, quantum mechanics increasingly defines what is possible. Power consumption, heat dissipation, and processing speed are all constrained by quantum principles. Landauer's principle, which links information erasure to energy dissipation, involves Planck's constant indirectly through thermal and quantum limits. The realization that information itself has physical consequences highlights the deep connection between computation and fundamental physics. The emergence of quantum computing represents perhaps the most direct technological expression of Planck's constant's legacy. Quantum bits exploit superposition and entanglement to perform computations beyond the reach of classical machines. The manipulation of quantum states relies on precise control of energy levels, phases, and interactions, all governed by H. While still in its early stages, quantum computing promises to revolutionize cryptography, materials science, and complex system modeling, extending the technological impact of Planck's constant into the future. Even consumer technologies reflect quantum principles shaped by Planck's constant. Touchscreens, digital cameras, LEDs, and wireless communication systems all rely on quantized interactions between electrons and photons. The reliability, efficiency, and miniaturization of these devices depend on the predictability imposed by quantum laws. What once seemed like exotic physics has become embedded in everyday objects, often unnoticed yet indispensable. The technological significance of Planck's constant also reshaped engineering philosophy. Rather than fighting quantum effects as sources of noise or error, engineers learned to harness them. Quantum tunneling, coherence, and discrete energy levels became tools rather than obstacles. This shift mirrors the broader transformation in physics itself, where embracing quantization led to deeper understanding and greater control over nature. Perhaps most striking is how a constant with no dimensions of length, mass, or time directly determines the limits of technological progress. It defines the smallest action that can occur, the minimum uncertainty that must be tolerated, and the scale at which classical approximations fail. As devices become smaller, faster, and more precise, they inevitably confront the boundaries set by Planck's constant. These boundaries are not arbitrary. They are fundamental, woven into the structure of reality. From the first transistor to the most advanced quantum sensor, Planck's constant has guided technological evolution with quiet authority. It does not dictate specific designs or inventions, but it defines the rules within which all designs must operate. Understanding those rules has allowed humanity to transform abstract quantum principles into practical tools that shape society. What began as a solution to a theoretical puzzle now underlies the digital, medical, and communication technologies that sustain modern civilization. Planck's constant acts as the hidden architect of this transformation, ensuring consistency, stability, and predictability across countless applications. Its presence in technology is a testament to the power of fundamental science to reshape the world in ways its originators could scarcely imagine. As technology continues to advance, the influence of Planck's constant becomes even more pronounced, not less. Each new generation of devices pushes closer to the fundamental limits imposed by quantum mechanics, and with every such approach, the constant that once seemed abstract emerges as a practical constraint shaping engineering decisions. In this regime, progress is no longer governed solely by ingenuity or materials science, but by the immutable rules encoded in the quantum fabric of reality. One of the clearest manifestations of these limits appears in miniaturization. As electronic components shrink toward atomic dimensions, electrons can no longer be treated as localized particles moving through wires. Their wave nature, governed by Planck's constant, becomes dominant. Quantum tunneling allows electrons to leak across insulating barriers, introducing noise, power loss, and errors. While tunneling can be exploited in certain devices, it also imposes a hard limit on how small and efficient classical electronic components can become. Engineers must now design systems that balance performance with the unavoidable consequences of quantized action. Thermal management offers another example of quantum constraints at work. Heat, at its most fundamental level, is carried by quantized excitations such as phonons and electrons. The flow of thermal energy through materials is governed by quantum statistics and energy quantization. As devices operate at higher speeds and densities, controlling heat becomes increasingly difficult. Planck's constant defines the minimum energy exchanges involved in these processes, placing lower bounds on power dissipation and cooling efficiency. These limits are not technological shortcomings, but intrinsic features of nature. The growing importance of quantum coherence further highlights the reach of Planck's constant in advanced technologies. Coherence refers to the maintenance of well-defined phase relationships between quantum states. In many emerging technologies, including quantum sensors and quantum computers, preserving coherence is essential for functionality. The timescales over which coherence can be maintained are influenced by interactions that involve energy exchanges quantified by H. Environmental disturbances, thermal noise, and material imperfections all disrupt coherence by inducing transitions governed by quantum rules. Understanding and mitigating these effects requires deep engagement with the principles encoded in Planck's constant. In quantum communication, the discrete nature of photons provides both security and reliability. Quantum cryptography exploits the fact that measuring a quantum state inevitably disturbs it, a consequence of quantized energy exchange. Any attempt to intercept a quantum communication channel leaves detectable traces, ensuring secure information transfer. The effectiveness of these protocols depends on precise control of photon states and energies, again determined by Planck's constant. As global communication infrastructure evolves, quantum, secure channels may become essential, embedding H even more deeply into societal systems. Metrology, the science of measurement, has been transformed by quantum principles in ways that place Planck's constant at center stage. The redefinition of fundamental units in terms of universal constants reflects a profound shift in how humanity understands measurement. By fixing the value of Planck's constant, mass can be defined through electromagnetic processes rather than physical artifacts. This approach ensures stability and universality, linking everyday measurements to fundamental laws. Precision manufacturing, scientific research, and global trade all benefit from this quantum-based framework. Advanced sensing technologies continue to push the boundaries of what can be detected. Quantum enhanced sensors exploit superposition and entanglement to surpass classical limits of sensitivity. Gravitational wave detectors, for example, rely on laser interferometry with sensitivity so extreme that quantum noise becomes a limiting factor. Reducing this noise requires manipulating quantum states of light, such as squeezed states, whose properties are governed by Planck's constant. The detection of spacetime ripples from distant cosmic events, thus depends on controlling quantum fluctuations dictated by H. In medicine, quantum technologies are poised to move beyond imaging into diagnostics and therapy. Techniques that manipulate quantum states of atoms and molecules may enable highly targeted treatments and ultrasensitive detection of disease markers. The energy scales involved in these processes are quantized, ensuring selectivity and minimizing collateral damage. As medical science increasingly intersects with quantum physics, Planck's constant will remain a guiding parameter, ensuring precision at the smallest scales. The intersection of quantum physics and materials science continues to yield new possibilities. Topological materials, whose properties arise from global features of their quantum states, exhibit robust behavior resistant to local disturbances. These materials owe their unusual properties to quantized phases and energy levels governed by Planck's constant. Potential applications include fault-tolerant electronics, efficient energy transport, and stable quantum devices. The discovery and engineering of such materials reflect a growing ability to harness quantum principles rather than merely accommodate them. Quantum simulation represents another frontier shaped by Planck's constant. By constructing controllable quantum systems that mimic more complex ones, scientists can explore phenomena that are otherwise computationally intractable. These simulations rely on precise manipulation of quantum states, with energy scales and dynamics set by H. Applications range from understanding height, temperature, superconductivity, to modeling chemical reactions and exotic phases of matter. Through quantum simulation, Planck's constant becomes a tool for exploring realms of physics beyond direct experimental reach. Even artificial intelligence and machine learning, fields often associated purely with software, may feel the influence of quantum principles. Quantum enhanced algorithms could exploit superposition and entanglement to process information in fundamentally new ways. While still largely theoretical, such approaches depend on hardware that operates at quantum scales, where Planck's constant governs state evolution and information encoding. The future of computation may therefore be shaped by the same constant that once resolved a 19th century radiation problem. The sustainability of future technologies will also be influenced by quantum limits. Energy efficiency, information density, and processing speed are all bounded by fundamental principles tied to Planck's constant. Recognizing these limits encourages the development of technologies that work with nature rather than against it. Quantum-aware engineering aims to design systems that respect and exploit quantization, minimizing waste and maximizing performance within unavoidable constraints. On a philosophical level, the technological embodiment of Planck's constant challenges traditional distinctions between pure science and applied engineering. The constant serves as a reminder that practical innovation often flows from deep theoretical insight. What began as an abstract constant in a theoretical model now shapes the infrastructure of global society. This trajectory underscores the value of fundamental research and its capacity to produce transformative, unforeseen applications. As humanity ventures further into the quantum era, Planck's constant will continue to serve as both guide and gatekeeper. It defines what is possible, what is efficient, and what is fundamentally unattainable. Understanding its role allows scientists and engineers to navigate the boundary between ambition and reality, innovation and limitation. Far from being an obstacle, these limits provide a stable framework within which creativity can flourish. The technological future promises devices and systems that operate ever closer to the quantum boundary. In this regime, classical approximations fade, and Planck's constant stands revealed as a central organizing principle. Whether enabling ultra-precise measurement, secure communication, advanced computation, or new forms of energy control, its influence remains constant and unavoidable. In reflecting on this progression, it becomes clear that Planck's constant has reshaped not only physics, but the very way humanity interacts with the material world. It governs the behavior of electrons and photons that carry information, energy, and structure throughout modern society. Its presence ensures reliability, precision, and universality, qualities essential to technological progress. The journey from theoretical abstraction to technological foundation illustrates the profound interconnectedness of knowledge. A single constant, introduced to solve a narrow scientific puzzle, now underlies the devices that define daily life and the innovations that shape the future. Planck's constant stands as a quiet testament to the power of fundamental ideas to transform the world, guiding technology with a steady, invisible hand. At the deepest level, Planck's constant is not merely a number that appears in equations. It is a boundary marker that separates the intuitive world of human experience from the true underlying structure of reality. Long before its implications were fully understood, physics assumed that nature was smooth, continuous, and infinitely divisible. Space could be split into ever smaller distances, energy into ever finer amounts, and time into endlessly shrinking intervals. This assumption worked remarkably well for centuries, allowing scientists to describe planetary motion, mechanical systems, and electromagnetic waves with stunning accuracy. Yet hidden beneath this apparent continuity was a subtle graininess that only revealed itself when scientists dared to look closely enough. The emergence of Planck's constant forced a radical reassessment of what it means to observe, measure, and even define reality. At quantum scales, energy does not flow smoothly like water through a river, but arrives in discrete packets. Motion does not follow a single, well-defined path, but unfolds as a range of possibilities. Measurement itself becomes an active process that influences the system being observed. Planck's constant lies at the heart of all these phenomena, acting as the scale factor that determines how pronounced quantum effects become. One of the most profound implications of this constant is its role in limiting knowledge. In classical physics, uncertainty was viewed as a temporary problem, a consequence of imperfect instruments or incomplete information. With better tools and methods, it was believed that uncertainty could be reduced indefinitely. Quantum mechanics shattered this assumption. The uncertainty principle reveals that there are fundamental limits to how precisely certain pairs of physical properties can be known simultaneously. These limits are not technological shortcomings, but intrinsic features of reality, quantified directly by Planck's constant. This realization carries deep philosophical weight. It suggests that the universe is not a perfectly transparent machine waiting to be fully decoded, but a system that preserves ambiguity at its core. The act of measurement, constrained by h, does not simply reveal pre-existing properties, but participates in shaping outcomes. Reality at the quantum level is not fully independent of observation, challenging long-held assumptions about objectivity and determinism. Planck's constant also reshapes the concept of causality. In classical thinking, causes lead to effects in a clear, predictable sequence. If the present state of a system is known precisely, its future can be calculated exactly. Quantum mechanics replaces this certainty with probabilities. The evolution of quantum systems is governed by precise mathematical laws, yet the outcomes of individual events remain fundamentally unpredictable. Planck's constant determines the scale at which this probabilistic behavior dominates, ensuring that randomness is not merely apparent but woven into the fabric of existence. This probabilistic nature does not imply chaos or disorder. Instead, it introduces a new kind of order, one governed by statistical regularities rather than exact trajectories. Large collections of quantum events produce stable, predictable patterns, giving rise to the classical world humans experience daily. Planck's constant ensures that quantum uncertainty averages out at macroscopic scales, allowing chairs to remain solid, planets to follow stable orbits, and time to appear continuous. In this way, the constant acts as a bridge between two worlds, reconciling quantum indeterminacy with classical reliability. The relationship between Planck's constant and time reveals another layer of its significance. Energy and time are linked through quantum principles, imposing limits on how rapidly systems can change and how briefly energy states can exist. Extremely short-lived states involve large energy uncertainties, while long-lived states exhibit greater stability. This connection influences phenomena ranging from radioactive decay to the lifetimes of excited atomic states. Time, often perceived as a smooth and universal flow, acquires a quantum texture shaped by h. The role of Planck's constant in defining the smallest meaningful actions in nature also challenges intuitive notions of scale. Below certain thresholds, classical descriptions lose their meaning. Concepts such as precise position, exact momentum, or well-defined trajectories dissolve into probability distributions. Planck's constant marks the boundary at which new rules take over, ensuring consistency and coherence within the quantum domain. These insights extend beyond physics into broader questions about reality and existence. If the universe operates according to probabilistic rules at its foundation, what does this imply about causation, free will, and determinism? While physics does not answer these questions directly, Planck's constant forces them into serious consideration. It reveals that uncertainty is not merely epistemic, but ontological, embedded in the structure of the universe itself. The constant also influences how scientists think about information. In quantum mechanics, information is physical, carried by quantum states whose properties are constrained by h. There are limits to how much information can be packed into a given region of space or transmitted within a given time. These limits connect Planck's constant to thermodynamics, black hole physics, and the ultimate bounds of computation. Information, once considered an abstract concept, becomes a tangible quantity shaped by quantum laws. In cosmology, Planck's constant plays a crucial role in understanding the early universe. At extremely high energies and densities, quantum effects dominate gravitational interactions, requiring a framework that unites quantum mechanics with general relativity. Although a complete theory of quantum gravity remains elusive, Planck's scale quantities derived from h, the speed of light, and the gravitational constant define the regime where classical spacetime concepts break down. Near this scale, space and time themselves may be quantized, challenging conventional notions of geometry and continuity. The presence of Planck's constant in these extreme conditions highlights its universality. Whether describing the behavior of electrons in an atom or the dynamics of the cosmos moments after the Big Bang, the same constant governs the rules. This universality suggests a deep unity underlying seemingly disparate phenomena, reinforcing the idea that the universe operates according to a coherent set of principles across all scales. The conceptual shift introduced by Planck's constant also transformed scientific methodology. Physicists learned that intuition rooted in everyday experience is often unreliable at quantum scales. Mathematical formalism becomes essential, serving as a guide through a realm where classical analogies fail. Yet, even within this abstract framework, Planck's constant provides a grounding reference, ensuring consistency and interpretability across theories. As quantum mechanics matured, debates about its interpretation intensified. Questions about wave, function collapse, the role of the observer, and the meaning of probability remain unresolved. In every interpretation, however, Planck's constant remains central. It sets the scale of quantum effects and ensures agreement between theory and experiment. Regardless of philosophical stance, H stands as an empirical anchor, connecting abstract ideas to measurable reality. The constant's influence on human understanding extends beyond science into culture and philosophy. It symbolizes the limits of human knowledge and the humility required to confront them. The realization that nature resists complete predictability challenges the Enlightenment ideal of total rational mastery. Instead, it invites a more nuanced perspective that embraces uncertainty as a fundamental feature rather than a flaw. At the same time, Planck's constant demonstrates that limits can be productive rather than restrictive. By revealing where classical ideas fail, it opens new avenues of exploration and innovation. Quantum technologies, philosophical insights, and new forms of scientific inquiry all arise from engaging with the boundaries defined by H. In this sense, the constant is not a barrier but a gateway to deeper understanding. The interplay between determinism and probability, continuity and discreteness, knowledge and uncertainty defines much of modern physics. Planck's constant sits at the center of this interplay, shaping the language and concepts used to describe reality. It forces scientists to think carefully about what can be known, how it can be known, and what questions remain fundamentally open. As humanity continues to explore the universe, both experimentally and theoretically, the lessons encoded in Planck's constant remain as relevant as ever. They remind us that reality is richer and stranger than intuition suggests, governed by principles that challenge comfort but reward curiosity. The constant stands as a quiet yet profound symbol of this deeper order, guiding inquiry while preserving mystery. This dual role, as both constraint and inspiration, defines the enduring legacy of Planck's constant. It reshaped physics, altered philosophy, and redefined humanity's relationship with the universe. Far from being a mere numerical factor, it represents a turning point in how reality itself is understood, marking the moment when science acknowledged the limits of certainty and embraced the quantum nature of existence. As these ideas settled into the foundations of modern physics, the meaning of reality itself began to shift. Planck's constant quietly redefined what it means for something to exist in a definite state. At the quantum level, systems are not described by fixed properties, but by ranges of potential outcomes. This is not because nature is incomplete or poorly defined, but because the universe operates within constraints that forbid absolute precision. The constant determines the scale at which these constraints apply, ensuring that ambiguity is not an accident but a built-in feature of existence. This insight fundamentally alters how scientific truth is understood. In classical science, truth was associated with exact values and deterministic laws. A complete description of a system meant knowing its state precisely at every moment. Quantum theory replaces this notion with one where truth is statistical, expressed through probabilities that can be tested and confirmed only across many events. Planck's constant governs the width of these probability distributions, defining how sharply or loosely reality can be pinned down. The implications of this shift reach beyond physics into epistemology, the study of knowledge itself. If the universe does not permit complete certainty, then knowledge must be framed in terms of likelihoods rather than absolutes. This does not weaken science. It strengthens it by aligning expectations with reality. Planck's constant ensures that predictions are honest, reflecting the true limits imposed by nature rather than the aspirations of human reasoning. Another profound consequence emerges in the relationship between observer and observed. In quantum mechanics, observation is not a passive act. Measuring a system involves an exchange of energy and momentum, and this exchange cannot be made arbitrarily small. The minimum disturbance introduced by any measurement is set by Planck's constant. As a result, the observer becomes an inseparable part of the phenomenon. Reality at the quantum level is not fully independent of interaction, challenging the classical ideal of detached observation. This interconnectedness gives rise to debates about the nature of objectivity. If measurements influence outcomes, can there be an observer and dependent reality? Different interpretations of quantum mechanics offer varied answers, yet all agree on the empirical role of Planck's constant. It defines the unavoidable backaction of measurement, ensuring that the limits of observation are universal rather than subjective. The constant also shapes the way time and change are understood. Quantum transitions occur in discrete steps, with energy differences linked to frequencies by h. This relationship implies that change itself is quantized at fundamental scales. Processes do not unfold smoothly, but through transitions between allowed states. While these steps are imperceptible at everyday scales, they govern the dynamics of atoms, molecules, and subatomic particles. Time, in this view, acquires a granular structure influenced by quantum constraints. In the realm of identity and individuality, Planck's constant contributes to the indistinguishability of quantum particles. Electrons, photons, and other fundamental entities do not possess unique labels or trajectories. Their behavior is governed by symmetry principles and statistical rules rooted in quantum mechanics. The inability to distinguish identical particles is not a practical limitation, but a fundamental feature enforced by the quantum framework. This challenges classical notions of individuality and separateness, suggesting a more relational understanding of existence. These ideas resonate with broader philosophical traditions that emphasize interconnectedness and impermanence. While physics does not endorse specific metaphysical doctrines, Planck's constant invites reflection on the nature of boundaries, identities, and change. It reveals a universe where distinctions blur at fundamental levels, and where stability emerges from underlying uncertainty. The constant's role in defining the limits of spacetime becomes especially significant when considering gravity. At scales where quantum effects and gravitational effects are both strong, classical descriptions of spacetime break down. Planck's scale quantities suggest that space and time themselves may be subject to quantum fluctuations. In such regimes, geometry is no longer fixed but dynamic and uncertain. Although a complete theory of quantum gravity remains a goal rather than an achievement, Planck's constant provides essential clues about where and how new physics must emerge. Black holes offer a striking illustration of these ideas. The interplay between gravity, quantum mechanics, and thermodynamics reveals deep connections between information, entropy, and spacetime. The quantization of energy and the limits on information density, both influenced by Planck's constant, play crucial roles in understanding black hole radiation and evaporation. These phenomena challenge classical intuitions and suggest that information is preserved in ways that transcend traditional spacetime descriptions. The constant also informs the ultimate limits of measurement and observation. There are bounds on how accurately distances, times, and energies can be measured without collapsing systems or creating new ones. These limits are not merely practical, but fundamental. They imply that there is a smallest meaningful scale beyond which questions lose operational significance. Planck's constant helps define this boundary, ensuring consistency and coherence in physical descriptions. As science advances, the integration of quantum principles into broader frameworks continues to reshape understanding. Fields such as quantum thermodynamics explore how classical concepts like heat, work, and entropy behave in regimes governed by H. These studies reveal subtle effects, such as fluctuations and correlations, that have no classical analogues. The constant thus extends its influence into domains once thought fully understood. In the context of human perception and cognition, the implications are subtle yet intriguing. While the brain operates at scales far above the quantum domain, the principles that govern matter and energy at all levels ultimately trace back to quantum laws. Planck's constant ensures that the physical substrate of thought obeys probabilistic rules at its foundation. This does not imply that consciousness itself is quantum in nature, but it highlights the continuity between fundamental physics and complex systems. The cultural impact of Planck's constant reflects its symbolic power. It represents the moment when science acknowledged inherent limits and embraced uncertainty as a fundamental aspect of reality. This shift resonates with modern perspectives that value complexity, ambiguity, and openness. The constant becomes a metaphor for the balance between knowledge and mystery, precision and humility. Despite its abstract nature, Planck's constant remains grounded in empirical reality. Its value is measured with extraordinary precision, and its effects are observed in countless experiments. This combination of conceptual depth and experimental reliability exemplifies the strength of modern physics. It shows that even the most counterintuitive ideas can be rigorously tested and confirmed. The endurance of Planck's constant across theories and scales underscores its foundational role. Whether in quantum mechanics, quantum field theory, or emerging approaches to quantum gravity, H remains indispensable. It anchors mathematical structures to physical reality, ensuring continuity and coherence across diverse domains. Looking ahead, future discoveries may deepen or revise our understanding of quantum phenomena, yet Planck's constant is likely to remain central. Any new theory must reproduce its effects in appropriate limits, just as quantum mechanics recovers classical behavior at large scales. The constant thus serves as a benchmark against which new ideas are measured. In reflecting on the broader narrative of science, Planck's constant stands as a reminder that progress often begins with confronting anomalies. A small discrepancy in radiation theory led to a constant that transformed physics and reshaped humanity's world. This history highlights the power of questioning assumptions and embracing unexpected results. Ultimately, Planck's constant teaches that reality is not infinitely malleable to human desire for certainty. It imposes boundaries that are neither arbitrary nor negotiable. Yet within these boundaries lies immense richness, diversity, and possibility. By revealing the quantum structure of the universe, the constant opens a window onto a deeper level of order, one that blends necessity with chance. The universe, as revealed through Planck's constant, is not a clockwork machine nor a realm of pure chaos. It is a dynamic system governed by precise laws that allow for uncertainty and creativity. This balance gives rise to complexity, stability, and evolution across scales. From atoms to galaxies, the imprint of H can be found shaping patterns and processes. In this sense, Planck's constant is more than a parameter of physics. It is a statement about the nature of reality itself. It affirms that limits are fundamental, that knowledge has boundaries, and that within those boundaries lies a universe of profound depth. The constant invites humility, curiosity, and wonder, reminding humanity that understanding the universe is an ongoing journey rather than a completed task. As this journey continues, Planck's constant remains a steadfast guide, quietly defining the contours of what can be known and what must remain open. Its legacy is not only scientific but philosophical, shaping how reality, knowledge, and existence are understood. In acknowledging its role, humanity takes another step toward understanding its place within a universe that is at once precise, mysterious, and endlessly fascinating. As scientific understanding deepens, Planck's constant begins to reveal an even more profound role. It is not only a bridge between classical and quantum physics, but also a key to understanding the ultimate limits of reality itself. At extreme scales, where energy, space, and time converge, this constant defines the boundary between what can be described using known physical laws and what lies beyond current comprehension. In this sense, it stands at the edge of human knowledge, marking the point where familiar concepts dissolve and new frameworks are required. One of the most striking implications of Planck's constant emerges when considering the smallest measurable units of nature. By combining it with the speed of light and the gravitational constant, physicists derive fundamental scales of length, time, and energy. These scales suggest that there is a minimum meaningful size to space, and a smallest possible interval of time. Below these thresholds, the very notion of distance or duration may lose its meaning. Space may no longer be smooth, and time may no longer flow continuously. Instead, reality could be composed of discrete elements woven together by quantum principles. This idea challenges centuries of assumptions about the nature of the universe. Classical physics treated space as an infinite stage and time as an ever-flowing river, unaffected by the events unfolding within them. Quantum insights, guided by Planck's constant, suggest a radically different picture. Space and time may themselves be dynamic, fluctuating entities subject to uncertainty. At extremely small scales, spacetime could behave less like a fabric and more like a restless sea of quantum activity. The consequences of this perspective are especially significant in the study of gravity. General relativity describes gravity as the curvature of spacetime caused by mass and energy, a theory that works extraordinarily well at large scales. Quantum mechanics, however, governs the behavior of particles and fields at the smallest scales, where Planck's constant dominates. When these two frameworks intersect, contradictions arise. Resolving these contradictions requires a theory that respects both quantum principles and gravitational effects, a goal that has driven decades of research into quantum gravity. In this quest, Planck's constant serves as a guiding parameter. It defines the scale at which quantum fluctuations of spacetime become unavoidable. At such scales, spacetime may no longer be continuous, but instead composed of discrete units or networks. Concepts like position, distance, and geometry may only exist as approximate descriptions, emerging from deeper quantum structures. While experimental access to these scales remains beyond current technology, theoretical models consistently point toward Planck's constant as the key ingredient in any successful unification. Black holes provide a natural laboratory for exploring these ideas. Within their extreme gravitational fields, quantum effects become significant in unexpected ways. The realization that black holes emit radiation was a direct consequence of applying quantum principles to curved spacetime. This radiation implies that black holes are not entirely black, and that they possess temperature and entropy. These properties depend on Planck's constant, linking quantum theory, thermodynamics, and gravity in a single framework. The entropy of a black hole, proportional to the area of its event horizon, suggests that information is stored in a highly compressed, quantized form. This insight has led to profound questions about the nature of information and its role in the universe. If information is physical, as quantum theory suggests, then Planck's constant governs its fundamental units. The limits on information storage and transmission become constraints on the structure of reality itself. These ideas extend into cosmology, where the early universe presents conditions of extreme energy and density. Near the beginning of cosmic history, quantum fluctuations governed by Planck's constant may have played a decisive role in shaping the large-scale structure of the universe. Tiny variations in energy density could have been amplified by cosmic expansion, eventually giving rise to galaxies, stars, and planets. In this way, the constant may be indirectly responsible for the very existence of structure in the cosmos. The inflationary models of cosmology rely heavily on quantum principles to explain the origin of cosmic irregularities. These fluctuations are not random noise, but statistically constrained features rooted in quantum mechanics. Planck's constant sets the scale of these primordial variations, ensuring consistency between theoretical predictions and astronomical observations. The patterns observed in the cosmic background radiation serve as a fossil record of quantum processes that occurred billions of years ago. Beyond cosmology, Planck's constant influences the limits of knowledge itself. It defines the smallest measurable changes in energy and action, setting bounds on experimental precision. No matter how advanced technology becomes, these limits cannot be surpassed. This realization reframes scientific ambition, shifting the focus from achieving infinite precision to understanding the fundamental constraints imposed by nature. The concept of a minimum measurable scale has philosophical implications as well. It suggests that the universe may not be infinitely divisible, contradicting ancient notions of continuity. Instead, reality could be fundamentally digital, composed of discrete units governed by quantum rules. While this does not imply simplicity, it does suggest a structured foundation beneath apparent complexity. In theoretical physics, efforts to describe reality at these scales often involve abstract mathematical frameworks. These models challenge intuition, relying on concepts such as higher dimensions, networks, or quantum states of geometry. Despite their diversity, all such approaches must incorporate Planck's constant in a fundamental way. It ensures that quantum behavior emerges naturally and that classical descriptions are recovered at larger scales. The role of Planck's constant in these theories underscores its universality. It is not tied to any specific particle, force, or interaction, but applies equally across all domains. This universality hints at a deep unity underlying physical laws. Whether describing the behavior of a photon, the structure of spacetime, or the evolution of the universe, the same constant governs the rules. The search for a unified theory is not merely a technical challenge, but a conceptual one. It requires rethinking basic assumptions about space, time, and causality. Planck's constant forces physicists to confront the possibility that familiar concepts are emergent rather than fundamental. What appears continuous and deterministic at everyday scales may arise from discrete, probabilistic processes at deeper levels. This perspective reshapes the meaning of explanation in physics. Instead of reducing phenomena to smaller and smaller components indefinitely, explanation may involve identifying the principles that govern emergence across scales. Planck's constant plays a central role in this process, marking the transition points where new behaviors arise. Even without a complete theory of quantum gravity, the influence of Planck's constant continues to guide experimental and theoretical work. Precision measurements probe ever smaller distances and higher energies, testing the boundaries of known physics. While direct access to Planck's scale phenomena remains elusive, indirect effects may offer clues about the structure of reality at its most fundamental level. The constant also serves as a reminder of the provisional nature of scientific knowledge. Just as classical physics was once believed complete, modern theories may one day be superseded by deeper insights. Yet any future framework must still account for the successes of existing theories and reproduce their predictions. Planck's constant stands as a fixed reference point in this evolving landscape, anchoring new ideas to established results. In this way, the constant embodies both continuity and change. It represents a stable element within a dynamic process of discovery. As theories evolve, the meaning of Planck's constant may deepen, revealing new connections and interpretations. Its numerical value remains fixed, but its conceptual significance continues to expand. Ultimately, Planck's constant invites reflection on the limits and possibilities of human understanding. It shows that nature is not infinitely transparent, but structured in ways that resist complete capture. Yet within these limits lies a remarkable coherence, a universe governed by principles that can be discovered, tested, and understood, at least in part. The pursuit of knowledge at the edge of physics is driven not only by curiosity, but by a desire to understand our place in the cosmos. By revealing the quantum foundations of space, time, and matter, Planck's constant connects the smallest scales of existence to the largest questions of meaning and origin. It reminds us that even the most abstract ideas can have profound implications for how reality is conceived. As scientific exploration continues, the constant remains a silent guide, marking the frontier between the known and the unknown. It challenges assumptions, inspires innovation, and anchors speculation in measurable reality. In doing so, it shapes the ongoing effort to understand the universe not just as it appears, but as it truly is beneath the surface of everyday experience. As exploration into the quantum foundations of the universe advances, the practical and theoretical influence of Planck's constant becomes ever more apparent. While originally conceived to resolve a puzzle about radiation, the constant now serves as a universal ruler for the smallest meaningful units of action, energy, and momentum. It dictates the scales at which classical intuition fails, and new laws must be invoked. At these scales, the universe reveals a subtle complexity. What seems continuous from afar is, at its core, composed of discrete quanta that obey strict probabilistic rules. One of the most striking applications of this principle emerges in high-energy physics. Particle accelerators probe distances and energies where Planck's constant is essential in interpreting results. Collisions between particles occur at such small scales that quantum fluctuations cannot be ignored. The allowed energy states, decay rates, and interaction probabilities are all determined by quantization principles, ensuring that predictions match experimental observations. Every detector reading, every particle track, is shaped by the limits imposed by Planck's constant. Even in particle physics, these quantum boundaries impose deep constraints. The very notion of a particle's position and momentum is subject to uncertainty, a limit defined by h. This uncertainty governs the design of experiments and the interpretation of data. Without acknowledging these boundaries, conclusions about subatomic processes would be fundamentally flawed. Thus, Planck's constant is not a theoretical abstraction, but a practical necessity for accurately describing the microscopic world. The constant's influence extends into the emergent field of quantum cosmology. Here, researchers attempt to understand the origin and evolution of the universe using the principles of quantum mechanics. The early universe, a high-energy, high-density environment, is governed by phenomena where Planck's constant plays a central role. Quantum fluctuations during this epoch seeded the formation of cosmic structures, such as galaxies and galaxy clusters. Tiny variations in energy, magnified by cosmic inflation, became the blueprint for the large-scale universe we observe today. Without h setting the scale of these fluctuations, the universe might have evolved into a featureless expanse. In addition, the constant governs the behavior of matter under extreme conditions, such as those found in neutron stars. At such high densities, quantum degeneracy pressure arising from the Pauli exclusion principle and energy quantization supports the star against gravitational collapse. Planck's constant defines the minimal allowed spacing in energy levels for fermions, determining how matter resists compression. This same principle informs our understanding of white dwarfs and other compact objects, linking quantum behavior to astrophysical phenomena. Theoretical work on quantum gravity consistently identifies Planck's scale limits as a critical frontier. The Planck length, time, and energy mark thresholds beyond which conventional spacetime concepts break down. Here, ideas of geometry, causality, and continuity must be rethought. While these scales remain experimentally inaccessible, they provide a framework for constructing self-consistent theories that unify quantum mechanics and general relativity. Any successful quantum gravity model must incorporate H in a fundamental way, ensuring that known quantum behavior emerges naturally at lower energies. Planck's constant also sets the scale for vacuum fluctuations and zero-point energy. Even empty space is filled with quantum activity, with particles and fields constantly fluctuating in and out of existence. These fluctuations have measurable effects, from the Casimir force to subtle contributions to cosmological phenomena. The energy of each quantum fluctuation is dictated by Planck's constant, highlighting how a single numerical value governs the unseen dynamism of the vacuum itself. These principles extend into the study of entropy and information. The universe's capacity to store and process information is limited by fundamental quantum constraints. Black hole thermodynamics illustrates this vividly. The maximum information a black hole can contain is proportional to the area of its event horizon, and the discrete nature of energy and action, defined by H, sets the minimal units of information. Such insights link Planck's constant to questions that transcend physics, touching on computation, knowledge, and the ultimate limits of observation. Quantum entanglement, another phenomenon shaped by Planck's constant, challenges conventional notions of locality and causality. Entangled particles maintain correlations regardless of distance, a feature that does not violate relativity but emerges naturally from the quantum framework. The energy scales, transition probabilities, and coherence times governing entanglement are directly linked to H. As technologies such as quantum teleportation and quantum communication advance, this constant remains central to predicting, controlling, and exploiting these phenomena. In practical technology, these quantum principles are not just theoretical curiosities, but foundational to innovation. Quantum computing, quantum cryptography, and precision measurement all rely on manipulating systems where Planck's constant defines energy differences, timing, and interactions. Coherence, tunneling, superposition, and entanglement are all controlled through the same rules that Planck first introduced in the context of Blackbody radiation. Without this understanding, modern quantum technologies would be impossible. Even at the interface of classical and quantum domains, the constant imposes subtle constraints. Classical approximations work because H is extremely small relative to macroscopic scales. Yet as devices shrink and measurement sensitivity increases, quantum effects become unavoidable. Nanoscale engineering, quantum optics, and ultrafast spectroscopy all confront these limits daily. Engineers and experimentalists design around H, acknowledging its influence while exploiting its predictability. Philosophically, this reinforces a central lesson: limits are not deficiencies but structure. Planck's constant sets the framework in which nature operates. Its universality ensures that physical laws are consistent across all scales, from subatomic particles to cosmological structures. By understanding and respecting these limits, humanity gains access to a deeper, more coherent picture of reality. The constant also links energy, frequency, and time in ways that underpin modern measurement standards. Atomic clocks, laser systems, and spectroscopic techniques rely on transitions whose energies are determined by h. By defining the frequency of specific atomic transitions, timekeeping has achieved extraordinary precision, enabling GPS, satellite communications, and international synchronization. Here, the constant not only governs microscopic physics, but shapes global infrastructure and daily life. Moreover, Planck's constant offers a conceptual bridge to emerging fields such as quantum thermodynamics. Researchers investigate how classical notions of work, heat, and efficiency are altered when energy exchanges occur in discrete quanta. At microscopic scales, fluctuations dominate behavior, and h sets the minimal steps by which energy can change. These insights influence nanoengineering, molecular machines, and the understanding of life itself at cellular and molecular levels. At the frontier of physics, theorists explore even more abstract concepts where Planck's constant is central. Ideas such as holographic principles, quantum information in spacetime, and emergent gravity all require precise quantization to remain internally consistent. In these models, h defines the smallest action and energy units, ensuring that mathematical structures correspond to measurable reality. The constant thus anchors even the most speculative ideas in empirical foundations. The ongoing exploration of dark matter and dark energy may also invoke principles connected to Planck's constant. While these phenomena remain poorly understood, any quantum-based theory must respect the quantization of action and energy. H provides the scale for interactions, transitions, and fluctuations that could illuminate the nature of these mysterious components of the cosmos. In this way, the constant continues to shape inquiry at the edges of the known universe. Across all these domains, Planck's constant serves as both a limit and a guide. It defines what can happen, how precisely processes can occur, and the minimum scales at which nature expresses its discrete character. Far from being a hindrance, these boundaries allow scientists to predict, control, and innovate. By understanding the rules imposed by H, humanity can navigate the quantum realm with confidence and creativity. At its core, the constant exemplifies the profound interplay between theory and reality. It arose from a theoretical necessity, a solution to an empirical puzzle, and yet it governs both the minutest particles and the structure of spacetime itself. It exemplifies how abstract concepts, grounded in careful observation and reasoning, can have far-reaching consequences for technology, philosophy, and understanding of the universe. In reflecting on this influence, it becomes clear that Planck's constant is not just a parameter in equations, but a cornerstone of modern science. Its universality and precision provide a lens through which the microscopic and macroscopic worlds are connected. By revealing the discrete nature of energy, action, and information, it challenges assumptions, expands horizons, and shapes both our tools and our ideas. The constant also symbolizes a larger lesson about the pursuit of knowledge. Nature is not infinitely malleable to human expectations. There are fundamental structures that resist classical intuition, yet these structures offer pathways to deeper understanding. By engaging with the constraints defined by Planck's constant, humanity gains access to a universe of subtlety, coherence, and infinite possibility. As research continues, both experimentally and theoretically, Planck's constant remains central to the endeavor of physics. It provides a scale, a framework, and a standard against which all phenomena are measured. Whether probing the cosmos, designing advanced technology, or exploring the foundations of reality, the constant offers a stable reference in a universe that is simultaneously deterministic in law and probabilistic in manifestation. In this way, Planck's constant bridges the abstract and the tangible, the microscopic and the cosmic, the known and the unknown. It governs not only the particles and fields within atoms, but also the emergence of stars, galaxies, and the large-scale architecture of the universe. Its influence stretches from laboratory instruments to the structure of reality itself. By acknowledging its central role, humanity gains a profound perspective on the limits and possibilities of understanding. Planck's constant reveals that uncertainty, discreteness, and quantization are not impediments but essential features of nature. They provide structure, stability, and predictability within the probabilistic framework of quantum mechanics. They allow creativity, innovation, and exploration to occur safely within the boundaries of physical law. Ultimately, Planck's constant embodies the duality of constraint and opportunity. It defines the rules while enabling limitless exploration within those rules. It reminds humanity that the universe is comprehensible, yet infinitely richer than intuition suggests. Its discovery, interpretation, and application mark one of the most profound turning points in the history of science, transforming the way the world is understood and experienced. At the intersection of observation and theory, Planck's constant asserts itself as more than a mere numerical factor. It emerges as a fundamental principle shaping the very way the universe operates, from subatomic particles to cosmological structures. Its influence is felt in the behavior of energy, matter, information, and even the passage of time itself. As scientific investigation advances, it becomes increasingly clear that H is not confined to equations in textbooks, but governs the dynamics of reality at every scale where quantum principles hold sway. One of the most striking aspects of this constant is its role in determining the quantization of energy. In the classical view, energy was considered continuous, flowing without restriction from one system to another. Light waves could, theoretically, have any energy value depending on amplitude, and particles could occupy arbitrary energy levels. This assumption led to paradoxes when applied to Blackbody radiation, culminating in the ultraviolet catastrophe. Planck's introduction of a fundamental unit of action, linking energy to frequency, resolved this crisis by asserting that energy can only be exchanged in discrete packets, or quanta. This principle transformed the understanding of radiation, heat, and the very foundation of statistical mechanics. The implications extend far beyond thermal radiation. Quantization underlies the structure of atoms, determining allowed electron orbits and energy levels. Without Planck's constant, the periodic table would be meaningless, and the chemistry of life could not exist. Electrons cannot spiral into nuclei because energy is restricted to discrete values, a simple principle with enormous consequences. Each molecule, each chemical reaction, and each biological process owes its stability to the discrete nature of energy as dictated by H. From the simplest hydrogen atom to the most complex proteins, quantization defines the architecture of matter itself. Planck's constant also governs the wave-particle duality of matter. Particles such as electrons exhibit both particle-like and wave-like properties, with the wavelength inversely proportional to momentum and scaled by h. This duality underlies diffraction, interference, and other phenomena that are counterintuitive from a classical perspective. The ability to predict and manipulate these behaviors has led to technologies like electron microscopy, which can resolve structures far smaller than the wavelength of visible light, revolutionizing biology, materials science, and nanotechnology. Furthermore, the constant defines the limits of precision in measurement. The Heisenberg uncertainty principle demonstrates that position and momentum, or energy and time, cannot both be known with arbitrary accuracy. The product of these uncertainties is bounded by h, ensuring that quantum indeterminacy is not a matter of experimental limitation, but a fundamental property of nature. This realization reshapes not only scientific methodology, but also philosophical interpretations of knowledge, causality, and determinism. In a universe governed by h, certainty is replaced by probability, and the act of measurement becomes an interaction rather than a passive observation. The role of Planck's constant in governing quantum fluctuations is equally profound. Even in a vacuum, energy is not zero, but exists in the form of transient fluctuations that give rise to virtual particles. These fluctuations contribute to phenomena like the Casimir effect, Lamb shift, and spontaneous emission. The energy scales and temporal intervals of these fluctuations are defined by h, showing that the constant governs not only static properties of matter, but also dynamic processes at the most fundamental level. Space itself, even when empty, is alive with quantum activity dictated by this single number. In the realm of solid-state physics, Planck's constant dictates the behavior of electrons in materials, giving rise to quantized conductance, energy bands, and superconductivity. The allowed energies for electrons in a crystal lattice are determined by quantum conditions, leading to insulators, semiconductors, and metals with very specific properties. The design of microchips, lasers, and magnetic devices depends directly on an understanding of these quantized energy levels. The revolution in electronics and computing over the past century rests upon the foundation laid by the insight that energy is not continuous but quantized, a principle expressed through Planck's constant. Planck's constant also defines the dynamics of atomic transitions and photon interactions. The absorption or emission of light occurs only when the energy of the photon matches the difference between discrete energy levels in an atom. This fundamental rule underpins spectroscopy, lasers, and quantum optics. It allows scientists to probe the internal structure of matter with extreme precision and to develop technologies that harness light in controlled ways. Precision instruments that measure atomic clocks, GPS satellites, and photonics systems all operate by exploiting the quantized interactions dictated by h. In chemistry and biology, the constant's influence is no less profound. Molecular vibrations, rotational states, and chemical bond energies are all quantized. Enzymatic reactions, photosynthesis, and even vision depend on energy transfers that occur in discrete steps. The stability and reactivity of matter, the conversion of energy in living systems, and the transmission of signals in neurons all hinge on the principles set forth by Planck. The constant, invisible yet omnipresent, underwrites the very fabric of life. At larger scales, Planck's constant mediates the emergence of classical behavior from quantum rules. While quantum effects dominate at the atomic and subatomic level, macroscopic systems appear continuous and deterministic because the relative magnitude of h is vanishingly small. Yet it is precisely the presence of h that ensures classical behavior emerges correctly from quantum laws. This bridging function, connecting the quantum and classical worlds, underscores its centrality in understanding reality comprehensively. Without it, there would be no coherent transition from the microscopic to the macroscopic, and the familiar world would not arise naturally from underlying principles. Planck's constant also governs the interplay of time and energy. Short-lived quantum states correspond to broader energy uncertainties, while long-lived states exhibit more precise energies. This relationship underpins spectroscopy, nuclear transitions, and particle decay. It imposes limits on the stability of excited states, influencing the lifetimes of atoms, nuclei, and molecules. It also provides insight into reaction dynamics, the behavior of quasi-particles, and the evolution of quantum systems over time. In quantum field theory, H sets the scale for quantization of fields. Every field, from electromagnetic to nuclear forces, has excitations that obey quantum rules, with energy increments proportional to H. These excitations include photons, gluons, and other fundamental particles. The existence, interactions, and decay of these particles are dictated by quantized energy exchanges, showing that the constant governs not only matter but also forces. Every prediction, from particle collisions to decay rates, relies on the precise value of H. Even in emerging technologies like quantum computing, Planck's constant remains central. Quantum bits, or qubits, operate on principles of superposition and entanglement, both of which are defined by the energy scales, transition rates, and coherence times that H determines. Controlling and maintaining qubits requires understanding the exact energy levels, tunneling rates, and interactions, all functions of the constant. Without H, quantum computation, quantum encryption, and quantum simulations would remain impossible in principle, not merely in practice. The constant also shapes the limits of information transfer and storage. In quantum communication, the discrete nature of photons ensures secure transmission, as any attempt to intercept or measure a quantum state disturbs it, revealing the presence of an eavesdropper. The energy, frequency, and coherence of these photons are all determined by H. In quantum metrology, the precision of measurements of time, length, and electromagnetic fields is bounded by fundamental quantum limits linked to Planck's constant. Thus, it governs the ultimate capabilities of communication, sensing, and measurement. In cosmology, Planck's constant contributes to understanding the early universe. Quantum fluctuations during inflation generated density variations that seeded galaxies and cosmic structures. These fluctuations are inherently probabilistic, with magnitudes set by the constant. As a result, H indirectly influenced the formation of stars, planets, and even the chemical elements necessary for life. The very patterns observed in the cosmic microwave background carry the imprint of quantum processes governed by this singular number. The constant's reach extends to theoretical explorations of spacetime and quantum gravity. At Planck scales, the graininess of space and time may become observable, and classical concepts of geometry may dissolve. Here, H defines the smallest meaningful units of action and energy, guiding theorists in constructing models where spacetime itself is emergent. Any viable theory must reconcile observed macroscopic behavior with the discrete quantum structure dictated by H. Philosophically, Planck's constant challenges assumptions about continuity, determinism, and absolute knowledge. It establishes that there are limits to precision and predictability built into the universe. Yet these limits are not constraints on inquiry. They are the framework within which exploration and understanding become possible. By delineating what is possible, H provides both structure and opportunity for discovery. In reflecting on its pervasive influence, it becomes clear that Planck's constant is not a peripheral figure in physics, but a central axis around which modern understanding revolves. It defines the behavior of particles, atoms, molecules, and light. It shapes the dynamics of matter and energy. It informs the emergence of classical phenomena from quantum rules. It governs the limits of knowledge, measurement, and information. And it influences cosmic evolution, from the earliest moments after the Big Bang to the formation of stars and galaxies. Without Planck's constant, the universe would be fundamentally different. Energy could vary continuously, matter might not form stable structures, and life itself could not emerge. The constant, imperceptible yet omnipresent, ensures the consistency and predictability of physical laws across all scales. It transforms abstract theory into practical reality, guiding technology, experimentation, and exploration. Through its subtle but universal role, H demonstrates that profound principles often emerge from attempts to solve specific puzzles. What began as a solution to Blackbody radiation now governs quantum mechanics, chemistry, solid-state physics, cosmology, and cutting-edge technology. The constant bridges microscopic and macroscopic worlds, links theoretical insight to experimental verification, and unites phenomena across space and time. Planck's constant is both a foundation and a frontier. It anchors our understanding of the quantum realm while pointing toward the mysteries that remain beyond current reach. It challenges, constrains, and enables, shaping the evolution of science and the tools humanity uses to explore the universe. Its discovery and application mark one of the most transformative moments in intellectual history, redefining the limits of knowledge and the scope of possibility. The reach of Planck's constant extends into the deepest conceptual questions about the universe, revealing how fundamental principles shape the structure and behavior of reality. At its core, H enforces limits on energy, action, momentum, and information that are not merely technical constraints but intrinsic features of the cosmos. These limits govern the evolution of systems across all scales, from the subatomic to the astronomical, creating a consistent framework in which the apparent complexity of the universe can emerge coherently from simple, universal rules. Quantum mechanics, grounded in H, reveals that events are not strictly deterministic. Instead, systems evolve according to probabilities constrained by the constant. This probabilistic character is evident in phenomena ranging from atomic transitions to radioactive decay. The predictability of large ensembles masks the underlying uncertainty of individual events, yet the constant ensures that even apparent randomness conforms to precise statistical laws. The stability of matter, the consistency of chemical reactions, and the reliability of atomic clocks all depend on this balance between indeterminacy and order. Planck's constant also defines the interaction between measurement and reality. Observing a quantum system invariably perturbs it, and the magnitude of this disturbance is dictated by H. This interplay is fundamental to understanding the limits of knowledge. Unlike classical systems, where observation can be made passively, quantum systems demonstrate that knowing and influencing are inseparable. The consequences are profound. The act of measurement is not merely revealing but participatory, shaping outcomes within the boundaries set by the constant. In modern physics, H functions as a unifying factor connecting disparate domains. Its presence is essential in particle physics, where it defines the allowed energies, momenta, and lifetimes of particles. In atomic and molecular physics, It governs electron transitions, rotational and vibrational levels, and spectroscopic signatures. In condensed matter, it determines band structures, superconductivity, and the behavior of nanoscale devices. Across all these scales, the constant provides a consistent rule that ensures coherence between theory and observation. The influence of H is particularly pronounced in technologies that harness quantum phenomena. Quantum computation, for instance, relies on superposition and entanglement, properties that derive from energy quantization and probabilistic evolution governed by the constant. Qubits operate in states defined by H, and their interactions, coherence times, and transitions are all constrained by its value. The design and operation of quantum computers, sensors, and secure communication networks would be impossible without understanding and applying the principles encoded by Planck's constant. In cosmology, H shapes the very origin of structure in the universe. During the inflationary epoch, quantum fluctuations generated density variations that seeded galaxies and larger cosmic structures. The magnitude of these fluctuations, their coherence, and their statistical distribution are all defined by the constant. Observations of the cosmic microwave background confirm that these predictions match reality, linking the physics of the very small to the architecture of the cosmos on the largest scales. The fingerprint of H is present in the distribution of matter and energy billions of years after the universe's birth. Planck's constant also constrains the behavior of extreme astrophysical objects. In neutron stars and white dwarfs, degeneracy pressure, arising from quantum principles and the discrete nature of energy, counteracts gravitational collapse. The allowed energy states of fermions, defined by H, prevent total compression and provide stability to these objects. Black holes, meanwhile, offer even more striking demonstrations. Their entropy, temperature, and radiation all hinge on quantum principles that rely on H. The constant ensures that even in the most extreme environments, physical laws retain coherence and predictability. Furthermore, H informs the limits of precision and measurement. In metrology, the constant underpins atomic clocks, spectroscopic standards, and definitions of units such as the kilogram and the second. Quantum mechanics dictates that there is a minimum uncertainty in measurements of energy, time, and position, governed by H. Precision instruments exploit these limits to achieve extraordinary accuracy, demonstrating the constant's practical relevance in addition to its theoretical importance. By defining what is measurable and to what precision, Planck's constant bridges theory and application, guiding both scientific understanding and technological development. At a deeper conceptual level, Planck's constant challenges classical assumptions about continuity and determinism. The universe is not infinitely divisible, nor is behavior strictly predictable at microscopic scales. Energy, action, and even angular momentum occur in discrete increments, with H setting the scale. Time and space, though appearing continuous at everyday scales, may themselves possess quantum granularity when examined at Planck scales. These insights reshape our understanding of causality, information, and the limits of human knowledge, highlighting that uncertainty is not a failure of measurement, but a fundamental feature of nature. Planck's constant also governs interactions at the quantum field level. Particles, forces, and excitations of fields all obey quantization rules. Photons, gluons, and other mediators of fundamental forces have energies, momenta, and lifetimes defined by H. In quantum electrodynamics, for example, precise predictions of particle interactions depend on the constant to ensure agreement with experiment. Across all fundamental interactions, Planck's constant ensures that theory is anchored to empirical reality, providing a framework that is internally consistent and experimentally verifiable. The constant's influence extends even into the philosophical domain. It implies that knowledge is inherently bounded, that certainty has limits, and that the universe is structured in ways that are not fully transparent. Yet within these boundaries lies order and predictability, allowing for coherent laws and emergent patterns. The discrete, probabilistic nature of quantum phenomena does not undermine science. It defines the arena in which inquiry and discovery are possible. Understanding these limits enables precision, creativity, and innovation. Planck's constant also plays a role in quantum information theory. The discrete energy levels and allowed transitions dictated by H determine how information can be encoded, transmitted, and processed at the quantum level. Quantum bits, entanglement, and superposition all rely on the quantization imposed by the constant. Even the limits on information density in physical systems, such as those inferred from black hole thermodynamics, trace back to H, demonstrating its relevance in the emerging field of quantum information science. The constant serves as a bridge between the microscopic and macroscopic worlds. While the effects of H are most evident at atomic and subatomic scales, it indirectly shapes phenomena at larger scales. Classical objects emerge from ensembles of quantum systems, and their stability depends on the quantized behavior of constituent particles. From the rigidity of a steel beam to the vibrations of molecules, H provides the foundation upon which macroscopic laws rest. Without it, classical behavior could not emerge reliably from the underlying quantum rules. In summary, Planck's constant is a universal regulator of nature. It dictates the scale at which quantum effects appear, determines the discreteness of energy and action, constrains measurement, and governs the evolution of systems. It is central to understanding atoms, molecules, solids, light, and the cosmos itself. Its presence unites diverse fields of study, from particle physics to cosmology, chemistry to quantum technology. Through H, the principles of quantum mechanics extend across space and time, connecting the infinitely small to the infinitely large and bridging the gap between theory and observation. As science continues to advance, the lessons encoded in Planck's constant remain vital. They remind researchers that limits are intrinsic, that uncertainty is fundamental, and that the universe is richer than intuition alone suggests. The constant represents both constraint and opportunity. It defines what is possible while enabling innovation, discovery, and exploration. Every new experiment, every new technological application, every new theoretical insight is shaped by this singular, pervasive number. In reflecting on its legacy, it becomes evident that Planck's constant is not merely a historical artifact of physics, but an enduring cornerstone of understanding. From the Blackbody radiation problem to the architecture of the cosmos, from the behavior of electrons to the limits of information, H provides the framework within which reality unfolds. It governs interactions, stabilizes structures, and delineates the scales at which classical intuition gives way to quantum principles. Without it, the coherence, predictability, and richness of the universe would be impossible. Ultimately, Planck's constant embodies the profound connection between the smallest units of action and the largest structures of existence. It is both a numerical parameter and a philosophical statement about the nature of reality, showing that limits, discreteness, and uncertainty are not obstacles but defining features. Through its influence, humanity has learned to navigate the quantum realm, understand the universe's architecture, and develop technologies that harness the hidden structures of nature. It stands as a testament to the power of insight, observation, and mathematical reasoning to reveal the underlying order of the cosmos. As the culmination of decades of exploration, Planck's constant emerges not simply as a number or a parameter, but as a lens through which the universe can be understood in its deepest sense. Its influence permeates the behavior of particles, the dynamics of fields, and the architecture of spacetime itself. From the microscopic interactions of subatomic particles to the evolution of galaxies across billions of years, the constant provides the foundation upon which reality is constructed. It unites phenomena across scales, offering a coherent framework that links the tangible and the abstract, the measurable and the conceptual. The profound significance of H becomes particularly evident when examining the nature of energy exchange. Classical physics, which preceded quantum theory, assumed that energy could be transferred continuously in arbitrary amounts. This assumption failed in explaining Blackbody radiation, where energy distributions predicted infinite emission at short wavelengths, the ultraviolet catastrophe. Planck resolved this paradox by proposing that energy could only be exchanged in discrete units proportional to frequency. This revolutionary idea not only solved an immediate problem, but also established a principle with sweeping implications. Energy is quantized. Every subsequent understanding of atomic structure, chemical bonding, and molecular dynamics builds upon this insight, making H a cornerstone of modern physics. In atoms, electrons occupy discrete energy levels, and transitions between these levels involve the absorption or emission of photons whose energies are determined precisely by Planck's constant. The stability of matter depends on these quantized states. Without them, electrons would collapse into nuclei, chemical elements would fail to exist as we know them, and the complex structures necessary for life would be impossible. Every reaction, every molecular interaction, and every biological process is underpinned by energy exchanges dictated by H, demonstrating that the constant shapes the very conditions for existence of complexity and life. The constant also governs wave-particle duality. Electrons and other particles exhibit both wave-like and particle-like properties, with the wavelength inversely proportional to momentum and scaled by h. This duality underlies interference, diffraction, and tunneling phenomena, which are central to fields ranging from materials science to nanotechnology. By dictating the relationship between momentum and wavelength, Planck's constant enables technologies such as electron microscopy, scanning tunneling microscopes, and advanced lithography, each of which reveals structures far smaller than classical optics could ever resolve. Planck's constant imposes fundamental limits on measurement. The Heisenberg uncertainty principle formalizes this by showing that pairs of complementary variables, such as position and momentum or energy and time, cannot both be precisely known. The product of these uncertainties is bounded by h, meaning that indeterminacy is an intrinsic feature of nature, not merely a limitation of instruments. This principle reshapes the philosophy of knowledge. It asserts that complete determinism is impossible at the microscopic scale, and that probability, rather than certainty, governs the evolution of quantum systems. Measurement, then, is not passive observation, but an interaction that inherently influences the system being observed. In condensed matter physics, Planck's constant determines the structure and behavior of materials. The allowed energy levels of electrons in crystals lead to the formation of bands, dictating whether a material behaves as a conductor, insulator, or semiconductor. This quantization underlies the development of electronic devices, lasers, and nanostructures, forming the foundation for the information technology revolution. The constant ensures that these behaviors are predictable, repeatable, and coherent across systems, allowing engineers and scientists to manipulate matter with unprecedented precision. Quantum fluctuations, another consequence of H, imbue even empty space with dynamic activity. The vacuum is never truly void, but teeming with transient particle, antiparticle pairs, and fluctuating fields. These zero-point energies have measurable effects, such as the Casimir force and contributions to atomic energy levels. The magnitude and timescales of these fluctuations are set by H, demonstrating that the constant governs phenomena at the most fundamental, seemingly intangible levels of reality. In astrophysics, H shapes the properties of extreme objects. Degeneracy pressure in white dwarfs and neutron stars arises from the quantization of energy states, preventing complete gravitational collapse. Black hole thermodynamics, including entropy and Hawking radiation, relies on quantum principles fundamentally tied to H. These effects reveal that even the most massive and energetic structures are influenced by the discrete nature of action and energy, bridging the realms of the very small and the extraordinarily large. Cosmologically, Planck's constant played a critical role in the early universe. During cosmic inflation, quantum fluctuations generated density variations that later became galaxies and large-scale structures. The amplitude and coherence of these fluctuations, set by H, are observable today in the cosmic microwave background, providing a direct link between fundamental quantum principles and the universe's macroscopic architecture. In this way, the constant indirectly shapes the cosmos itself, highlighting its universal significance. In theoretical physics, H is indispensable. Quantum field theory, which describes the behavior of fundamental forces and particles, relies on quantization rules established by Planck's constant. The creation, annihilation, and interactions of particles all involve energy quanta proportional to H. Any attempt to construct a unified theory of fundamental interactions or a quantum theory of gravity must preserve these quantization rules. The constant provides the scale for action, ensuring that the mathematics describing reality aligns with physical phenomena. Technologically, H underpins advances in quantum computing, cryptography, and metrology. Qubits exploit superposition and entanglement, behaviors dictated by quantized energy levels. Secure quantum communication depends on the discrete nature of photons, and atomic clocks achieve remarkable precision through energy transitions defined by H. Every experiment, device, and application operating at quantum scales is guided by the rules imposed by this constant, demonstrating that its relevance extends from theoretical abstractions to tangible innovations. The philosophical implications of Planck's constant are equally profound. It sets the ultimate limits of what can be known, measured, and predicted, reminding us that the universe is structured, but not infinitely transparent. Uncertainty is not a flaw, but an essential characteristic of nature. By revealing the granularity of energy and action, H challenges classical notions of continuity, determinism, and infinite divisibility. It encourages a perspective that blends rigor with humility, precision with openness, and curiosity with acceptance of fundamental limits. Planck's constant also mediates the emergence of classical behavior from quantum rules. While macroscopic systems appear deterministic, their stability and regularity arise from the collective behavior of vast numbers of quantum entities governed by H. Classical phenomena, rigid structures, continuous motion, and predictable forces emerge naturally from these underlying discrete rules, showing that the constant not only dictates microscopic behavior, but also ensures the coherence of the macroscopic world. Information theory and quantum mechanics intersect through Planck's constant. The discrete nature of energy levels constrains the storage, transmission, and processing of information. Quantum entanglement, teleportation, and secure communication all depend on H to define the allowed states and transitions of quantum systems. Even the limits of computation, dictated by the energy required to manipulate bits, trace back to the fundamental quantization of action established by the constant. At the frontier of physics, Planck's constant continues to guide exploration. Attempts to unify quantum mechanics with gravity, to understand spacetime at the smallest scales, and to probe phenomena near the Planck length and time rely on H as a fundamental benchmark. These extreme regimes reveal that space and time may themselves be discrete or emergent, with H defining the minimal meaningful intervals. Though experiments remain challenging, the constant provides a compass for theoretical development and conceptual clarity. In reflecting on its historical impact, Planck's constant represents a pivotal turning point. It emerged from an effort to resolve a specific empirical puzzle, yet its influence has reshaped nearly every domain of physics. It bridges theory and experiment, links microscopic and macroscopic scales, and unites classical and quantum descriptions. Its discovery demonstrates how a single conceptual innovation can transform our understanding of the universe and inspire generations of scientific inquiry. The constant also embodies the delicate interplay between constraint and possibility. By defining what is fundamentally allowed, it provides a framework within which the richness of the universe unfolds. Quantum mechanics, chemistry, solid, state physics, cosmology, and emerging technologies all operate within this framework. The constant ensures consistency and coherence, guiding both natural processes and human exploration. Far from restricting discovery, it enables precise control, prediction, and innovation. In the broader human context, Planck's constant symbolizes the power of insight, observation, and abstraction. It is a testament to the capacity of human thought to uncover hidden structures of reality, to discern patterns invisible to the senses, and to translate them into knowledge that transforms both understanding and capability. It bridges the concrete and the abstract, demonstrating that rigorous reasoning can reveal universal truths with practical and philosophical significance. As science progresses, Planck's constant remains central. It continues to anchor experimental design, theoretical models, and technological development. It defines the quantum world while informing the emergence of classical phenomena. It sets the boundaries of measurement, the limits of knowledge, and the rules for the behavior of matter, energy, and information. Its relevance spans the smallest scales of the subatomic world to the vast expanse of the cosmos. Ultimately, Planck's constant is more than a number in a formula. It is a principle that underlies the very architecture of reality. It ensures that energy is discrete, that probability governs microscopic events, that uncertainty is intrinsic, and that the universe operates according to consistent, observable rules. It connects the smallest quanta to the largest cosmic structures, guiding both understanding and application, theory and experiment. Its discovery represents one of the most profound leaps in human comprehension, reshaping physics, technology, and the philosophical understanding of the natural world.